of Nova, USA to come and conduct the proceedings.
Good morning, everybody. Welcome to the third day of the curtain raise. And I hope you all enjoyed yesterday as well as the day before and ready to take on today's presentations as well as other activities that are lined up here today. And our first speaker is none other than Dr. V.S. Prasad, head of the NCMRWF in Noida, New Delhi. Welcome, Dr. Prasad. Dr. Prasad is also a proud alumni of Andhra University, PhD with Professor Vittal Murthy Garu, and really reached the pinnacle of modeling in India and heading the National Center for Medium Range Weather Forecasts. So I think we will hear more from him on what they're doing on the coupled numerical weather prediction.
Thank you, Vijay.
So you have 25 minutes.
Thank you, Vijay, for giving introduction. And Sri Guru Pyo Namaha. And I have studied here in 87-89 batch MSc, and then did my PhD under Professor Vittal Murthy Garu, and presently working in NCMRWF. And today I'm going to talk about the coupled NWP system for seamless weather forecasting that is going to be operationalized soon at NCMRWF. And this is the first coupled model for the short and medium range forecasts. And so far, the coupled models are used for the seasonal forecasting and also for as a system model for the climate projections. And now we are at the stage of using the coupled model for even for the medium range forecast. And as you know, this IMD is going to celebrating now 150 years of its establishment, and similarly the Department of Meteorology Atmospheric Science is 75 years. So exactly in half of that one, almost 35 years, NCMRWF is also celebrating this year. And we are going to organize in November a workshop for commemorating these occasions. In this thing, I'm going to briefly tell about how the NWP evolved in India. This is the NWP process. Actually, we have for NWP, what is the most requirement is the data that we collect from all over the globe, that we come from the GTS and all those things, and the data assimilation system, and the NWP models. We have the many models that are working that one, and then forecast, and then we have to post-processing it and give it to the various users, including mainly it is for the Indian Meteorological Department. Along with Indian Meteorological Department, we are giving the specialized products for many fields, so that downscaling that one to the various purposes. For example, recently renewable energy is using that one. For that one also we are giving the specialized products, and also our defense forces, and also for nuclear energy, and all the type of specialized forecasts we are giving that one. And if you see that one, earlier we started with a single model in 1989. Thanks to NCEP, that time we have started a coarse resolution 150 kilometer GFS system. And from that we are evolved now. We are running a 12 kilometer global ensemble with 21 members. Such a means coarse resolution 150 kilometers to 12 kilometers, a 21 member ensemble system that we are running that one. And if you see that one, we have the two modeling systems. One is that seamless forecasting system of the You can see starting from the 330 meters for city forecasts, urban model for the Delhi, that one. Starting that one, we have the global coupled model up to 60 kilometers. So various models for the different purposes we have that one. And actually, the 330 meter DM model that was developed indigenously based on thing, we are able to give even the forecast for the runway. The visibility, especially it is very important in the winter time. We are giving the for flight operations. And you know, Delhi in winter we have the visibility very, very poor, less than this category for runway, that one. And so the visibility forecast and also that fog and pollution in the October to November are very important to the crucial for the things. So we have developed 330 meters, very high resolution, that one, and I will give more details of that one later. And we have that 1.5 kilometer high resolution mesoscale model for giving the forecast for the specialized for the Himalayan regions, mostly for the Amarnath Yatra time we are giving that forecast from July to August. And thanks to Dr. K.J. Ramesh Garu, that time he gave the inspiration for giving the Amarnath Yatra things. And so at that time we implemented the 1.5 kilometer specialized forecast for the Amarnath Yatra. And that 1.5 kilometer were downscaling to the 330 meter models for running that one. And then there is 4 kilometer regional model for giving the up to 72 hours regional forecast that we are giving high resolution then. And then 12 kilometer data we have deterministic and as ensemble data. When we implemented 2017, it is the highest resolution ensemble system in that time in the world. Now I think ICMW, they are taken more 9 kilometer ensembles, UK Met Office and that thing. When we implement that is highest resolution, that one. And that one we are giving to the forecast, to the specialized thing. And next, if you see that one, the skill of the forecast that we are, that our model starting from the 1989, we are improving the forecast skills by improvising the models from T80 to now 150 kilometers to now 12 kilometers. A lot of improvements are coming. You can see the improvements, that one. And the improvements are due to the change, due to the development of data assimilation things. We have putting the many efforts for using the more Indian data and also many specialized with our BIM. We have the second BIMSTEC center. So lot of regional data we are getting that from the BIMSTEC, all South Asian regions, that data, and also improving the assimilation schemes. For example, for India is the one of the countries which having the NWP as well as we have the NWP as well as the satellite program. So we are putting more efforts for Indian satellites designing as well as assimilation, that one. And our improvement is not only that shows that because of our changes it is very contemporary. If you compare to other models, it is carried by NCEP, our compared with other international models. You can see that our IMD GFS system with that one is almost equivalent to the set of other global models, except ECMWF. ECMWF is showing some more forecast skill. Our forecast skills are almost equivalent to NCEP or any other modeling systems. That is not just our claim. International centers, when they are comparing NCEP and other things, that showing that forecast skills are better and good, that one. And these improvements is possible because the support that government is giving in supporting us being the high computing systems. 1988, when you started it is 4 MFLOP systems. Now with 2.8 petaflop systems, and now within a few days we are going to get 8 petaflop systems. So the tremendous increase in the computing power from over the years that government is supporting to that one, and that is helping us to improve our forecast modeling systems, and also that India developed NKN network system through which we are able to get high bandwidth connectivity to the international centers, and we are getting very good data. And that also helping us to that one. If you see that one, the data growth, it is from 2002 to tremendous changes. We are getting at time 2 MB data that now we have crossed about 20 things, and from the FTP we are getting connections to to UMetcast and that thing, what we are able to get that the data real time. The satellite data is also improved tremendously. So the data growth from the 2014 onwards, you can see the tremendous growth of the data things. And also NCMRWF has a very good simulation team, and we are able to get AOLS data, that wind profiler data, that experiment, that UMetcast, UMetsat is in India. NCMR is the second center of ECMWF to operational the AOLS data, and also that Cosmic 2, and we are getting a lot of RO profiles data even from the private satellites of Spire, other things. These all data we are able to simulate, and we are able to now not only the model things, and parallelly with a lot of efforts we are getting the data. These two things helping us to improve the data quality very much. And if you see the Indian satellites, we have the starting from the INSAT program, we are getting, we have the many say Indian satellites are launched by ISRO, and we have NCMR made special efforts to assimilate the data, and also contributing to the quality of the improving the quality of the satellite data. For example, Kalpana, my PhD here with Vitramurthy Garu is the reassignment of the heights of the winds derived from the INSAT satellites, and thereby improving the quality of the winds. The height reassignment procedures that I developed that is being used, and Kalpana, and also Oceansat-T, it has MSMR data, and India is the only country used to the MSMR data, and similarly we are making a lot of efforts. And now we implemented even for assimilating direct satellite data, we are computing radiative transfer coefficients indigenously, and thereby we are doing the INSAT 3D and also microsat. The microsat 2B is the experimental satellite, light satellite for testing the vehicle, small satellite vehicle that ISRO launched, CubeSat, microsat 2B. Even that one also we were able to use. That is having the sensor just like some megatopic sapphire for giving the humidity. For that we have done radiative transfer modeling, and also we are able to, even experimental satellite data, we are also able to do that one. And for the scatterometer, NCMR made many efforts to show the improve the scatterometer skills. When the SCATSat 1 was there, Oceansat 2, when the scatterometer was first installed, the quality of the scatterometer data is not that bad. And we have made significant contributions to improve the quality of the scatterometer data. And now all over the globe, NWP centers are using SCATSat data and Indian scatterometer data very much. And so not only for the modeling purpose, even in the satellite, Indian satellite design, and using the satellite data and improving the, giving the feedback, and thereby improving the things, and SCMR playing significant role in the satellite data, Indian satellite data improvement and its assimilation. And few sensors, that megatropic sapphire and this scatterometer, Indian scatterometer is widely accepted all NWP centers, and many NWP centers operationally using the data of the scatterometer, this one. And now, as you said, that data initial conditions uncertainty is there because of the data related things, and also the model uncertainties, and we know definitely the uncertainty in the forecast. So earlier we are giving the definite forecast to the user, and we want to communicate the uncertainty in the model forecast. So by implementing the ensemble system, that we about 21 member ensembles, two systems. One is based on the GFS system, and one is based on the NCM system. We are running about 42 ensembles daily. Operationally, India is producing about 42 ensemble forecasts at 12 very high resolution, 12 kilometer, and that we are communicating to the things by even at a location specific also, we are communicating the uncertainty. Previously, we were giving the meteorograms with different values. Now we are giving the meteorograms with uncertainty and probability included. You can see the vertical bars at each point to the range of possible values, and their skills in terms of percentage. That thing we're communicating. And in the case of cyclones, dynamic probabilistic regions we are conducting, we are computing, and that is being given to the IMD and other sensors. So you can see the movement of cyclone along with the probability tracks that is certainly given that one, total that one given below. And if you see, the models now are able to, even recurvature also is being captured very well. And with all the probabilities, we are giving for a lot of for cyclones, we are giving the things, and the models are capturing not only genesis, even the tracks also reasonably well with the probabilistic range and everything we are able to give. And it resulted in the improvement of the cyclone forecast on region. Yesterday, Dr. Mahapatra is showing that how much improvement is there in the forecast of the cyclones. And the efforts at NCMRWF also resulted in improvement of this thing. And you can see in the case of this cyclone, we are able to see even the recurvature and the crossing. Even on the land also, we are able to capture up to the low very, very well. And as I said, we have the two ensemble systems that 42 members, 12 kilometers are coming. And we found that the GFS system is giving GEFS on some regions, and other UM-based NEPS also giving, in some regions, giving the better forecast. So to get best of this one, we implemented a grand ensemble with the two models, the NEPS and that thing, combined grand ensemble we are creating by following the process, the diagram, what we are showing that one. What we found is, if you are able to combine direct raw ensembles, because the biases of the models are not concerned, not able to give the best forecast. And what we are doing is we are removing the uncertain biases of the models, and then combining these two, giving to the better forecast, and giving the percentage of PQPFs for 10th and 50th, 90th percentiles, and giving the day 1 to day 10. And we found that there is a lot of improvement in that things, and also we're able to various regions, the weightages also we're giving here, and we are getting better forecast. This is the procedures that BMA and EMOS, and also we tested methods, different methods like this, to get the better forecast skills from using both the models. And you can clearly see in this the reliability forecast. You can see the pink line, which is showing the combined effect of the two models. Uncertainty and we ensemble things. We are getting the better skills even at 0.46 and extreme rainfall very well get. And the region wise also we are giving the weightages so that our forecast skills are better come for both the models. And we are giving the rainfall forecast probability PQPF from the grand ensembles, and similarly we are giving the temperature thing also from the grand ensemble. Temperature and whether these parameters, we are getting better forecast scales using the grand ensembles. Combining to that one, not only that each system has to be improved, each forecasting system has to be improved. So we going ahead with the coupled models for end of thing. And earlier we have the coupler at 65 kilometers. Now we are trying for 10 kilometers coupled models, and it has the components of ocean NEMO and atmosphere UM and land surface joules and sea ice. These components to the coupled oasis system, the system is in place for 65 kilometers, and we see the various data assimilation schemes. For land, we are using the ETKF, and for the atmosphere 4D-VAR and the sea ice NEMO. These three systems we are combining. And for the seasonal earlier this system was single system was 2019. We started this developing the coupled system, and it has a single model. And now we are running 55-member ensemble system for giving the seasonal and sub-seasonal forecast monthly thing. And if you see the skills of the seasonal forecast and also weekly forecast, we are getting the skills very much and very good. And for that purpose, we have the what we are employing. We have 71 member in cash, and every day every month at 1st, 9th, 17th, 25th, we are running the in cash for the with 16 member in cash we are running. Thereby we are getting the all members, time lagged members, and 7 members. This one totally we are getting 55 members, and we are getting the this is the model hint cast for the what we generated for 1998 2015. These we are using to generate ensembles, and we found that this skill of the forecast for seasonal compared with the ECMWF for seasonal forecast, we can clearly see that we are able to catch similar forecast skills as the ECMWF in that thing. And as we are running the coupled system, we are giving even the ocean anomalies and sea surface temperature anomalies to our ocean institutes, and this being very widely used as a byproduct of the coupled system, and that is being given to NCPOR and INCOAS and Indian Navy. They are using the byproducts of the coupled system for the seasonal forecast from the extreme. And if you see that the forecast scale up to date week 2, the skills are for sub-seasonal forecast. Up to week 2, we are getting the very good skill, and we are the forecast skills are very being appreciated. First day, Dr. Mahapatra given. He has appreciated the forecast skills that we are getting of the date 2, and up to week 2, and our system is able to forecast even delayed onset and also cyclone seasons also up to week 2. They are being forecasted very well. And this shows that delayed monsoon 2019, it is very well forecasted by the week 2. And that is this diagram in the first side. It shows that we are able to predict delayed monsoon by 7 days. That thing very well predicted, and you can see the rainfall anomaly for the cyclone region. That very high anomaly was forecasted even day 2 thing also. So delayed onsets in cyclones in the season that are very well predicted by the system. And this system we are using, as you shown, that Delhi model, the urban model, for that time we are using, and HRR systems we are using for nowcasting up to 0 to 6 hours, and short range we are using regional models up to 72 hours, and medium range we are using the medium range system, and as shown, extended and long range system, all the systems has been in place. And now what we are doing is combining the we are running the different system for the extended range seasonal. Now we are going to combine the coupled system, even for the medium range system also, and by bringing the coupled system resolution to 10 kilometers. This we are testing that one. Same thing what I told earlier is the conventional atmosphere has different assimilation skills and models for the things. For atmosphere, we have the 4D hybrid war NRC system, and ocean NEMO system, and land Joule system, and CEI 3DRF GAT. These systems are to combine to VOYASES, and this is the way we are running the design the system. The coupled model, weekly coupled simulations are run at every 6 hours, and they're combined it to go through a coupler good to give the initial conditions at that thing. And this system we tested this season parallelly at 10 kilometer resolution for this season JJS 2024, and it is continuing, and 2023 also for the 2 seasons we tested this system.
Prasad,
and
5 minutes.
Okay, and if for that one even data simulation for ocean also we have developed, and the various sets are using, and because of time, I'm skipping this one. And the system is performing very well. Even in the case of recent cyclone, Rimal, you can see this black line shows the IMD best track, and the various, you can see the condition, this is the observed track with the present operational model, and it is a coupled model. You can see the coupled model, even though their intensities we are not finding, not coming that accurately, but the track improvements very much found that one. You can see the track of the system of the recent remote cyclone very well brought out in with the coupled models, and even the positions, initial position of the system are very much improved, and at 144 hours also the range is increased, and if you see the 144 hours, the structure of the system was very much placed, and the deterministic system, there is a lot of shift is there, whereas the coupled system, it is able to bring the system at the right place with it is over-intensified in the in the operational system, whereas coupled system, the over-integration was reduced and somewhat reasonable with intensity. But of course, it is little bit weakened compared to the observable things, but it is near to observation. Over-integration was reduced, but it was little bit weakened. The position-wise, it was corrected very well, and with little weakening in intensity, it able to produce a better thing. Like that, where the track error, direct position error, CTE, there are improvements were found in that coupled system. And steering flows are also very well, upper level steering flow also very well captured in this system. And I'm skipping this one, total precipitable water, the improvements what are showing. So various fields, we checked that one. We were able to, even the rainfall also, the position up to day 5. We tested because of the computational things. We not done the whole 10 days. We done the system for the 5 days. Even the 5 days also position of heavy rainfall, very well. In the case of operational deterministic stick, you can see the rainfall band is shifting by the day 5, whereas in the case of coupled system, it is able to place at the same time, and the intensity also very well captured. And apart from that one, we are developing regional coupled system for coupled model for 4 kilometer resolution, and for this we are leading consortium for development of regional coupled model for the North Indian Ocean as the polar regions. NCMRWF is a leader for the consortium for developing that one. And apart from that one, we are seeing the observation impacts and improving that. We have the FSOA system, through which we are observing the impact of the data and the changes in the satellite sensors, and we are communicating any problem to the satellite operators, identifying the degradation of sensor for that thing, and we are continuously, from 2021 onwards, we are continuously running the FSOA system, and thereby showing the impact, changes in the impact, and also in the case of satellites, we are able to identify the degradation of sensors and helping satellite operators to take action for improving the satellite sensor. That one. And this is our way forward. We are going to do the next few in that one. And in the post-processing, the groups are working in putting AML in place for post-processing the data and getting the improving the forecast for agriculture, water, energy, defense. And Dr. Ashit was here. He is one of the person working with the renewable energy sector and also other applications to improve the forecast to AML and other techniques. Thank you.
Thank you, Dr. Prasad. Wonderful presentation, giving all the details about the NCMRWF and the progress that has been made with modeling systems. Quick questions or comments? Okay.
Anyway, for your excellent presentation, you have virtually predicting almost everything that user wants to know. For that, it is wonderful, excellent. And my comment is, it's more a comment, not a question. First of all, there are some common errors globally in many of these present day models. One of them is the double IT result that is there in your model, in ECMWF model, it is there even in ITM Earth System model. And I have seen a recent paper, 2024, May or June, in Bulletin of American Meteorology Society, a new approach, what you call, to improve the forecast compared to the Professor Krishnamurthy's multimodal forecast. There in Krishnamurthy's multimodal forecast, they don't change anything in the model. It's finally, it's an average. What more a statistical improvement, it's a more a statistical improvement. In the present type, they go on changing as you integrate. For example, you have 20 models. One of these 20 models is predicting better than of all of them compared to observations. So this particular model output, with that they correct all other models. Or as you proceed in the integration, they go on correcting all the models. It's not a continuous statistical average. It's a more a physical improvement. So my comment is, in addition to the present your extraordinary, fantastic work, probably it is important to find out the present defects and try to improve them through research. So that particular part, even in your way forward also, I see lacking. I see lacking. Because there are many things about the tropical cyclone, about the monsoon, dynamics. A lot of things are coming in the literature. And particularly this type of the work I am saying, it has corrected the double IT season. And there is no double IT season in their forecast anymore. That is something very new, and probably I will send you that paper, probably you can include. Thank you very much.
Thank you, Dr. Rao Garu.
Professor Prasad, presentation is very good. In CMW of reducing very good, and the coupled models also I have seen now. The salinity, sea surface salinity you have presented is the product of NEMO, or you have modified anything of that NEMO model?
It's product of NEMO.
Same NEMO model. So the same river runoff, everything you have as that of sea.
But we have additional efforts are putting a lot of data observations in that one and running the simulation system. And the simulation system here is completely different from what we are doing. And recently one of our scientists put even the soil salinity assimilation also. In the NEMO assimilation system, there is no salinity assimilation from the satellites. So observations are there. We use the SMOS data for assimilation of soil moisture and also salinity in that one. That is the effort that we changed. So that through assimilation, modeling, not much change is there, but assimilation definitely not many data is going in that one. And especially the satellite data, our own efforts were put that one, put the satellite. And original NEMO, there is no assimilation of the SMOS data.
Okay, that's good. That means your SMAP salinity is not going into that.
Yes.
Is going?
Yes, going.
So that will be more improvement in the salinity data.
Because of that assimilation schemes, the improvements.
Okay, good. Thank you very much.
Thank you. Thanks again for a wonderful presentation, Dr. Prasad. Excellent. So let's move on to another important presentation by Dr. K.J. Ramesh. We all know him as a friend of Andhra University, a product of Andhra University, a former Director General of India Meteorological Department, and a pioneer in advancing the science and technology in India, and has a lot of connections with the rest of the community as well. So welcome, Dr. Ramesh, and looking forward for your talk.
Thank you, Vijay, and congratulations to the university first. It is a great time of celebration and reassuring and rededicating our efforts with the students of next generation to take the advances much forward at par with global level by addressing the local problems. We are making efforts. You have seen modeling. You have so much of good models available. As Professor V.B. Rao said, effort is required to find out which is coming properly, which is not coming properly. So that is more important, and so many observations are there. Now, with all these models, not only Indian models run by IMD, IITM, and NCMRWF, and there are other global model products are also available online. So now it is a great challenge to extract which is good and which is not good. The which is good is in terms of skill scores, operational centers, operational organizations, they do. So what research community has to do it? So we have to see now the impacts. Now what is happening? We all know that global warming is increasing the intensity, frequency of extreme weather events. So that is happening because of warming makes atmosphere to hold more moisture. So more moisture means bigger clouds will give high intensity precipitation. So high intensity precipitation in short duration, which is doing impact and disturbing our normal life in many respects. So far we have been focusing efforts on minimizing the loss of life by improving the forecast of a cyclone systems. And then that was important because lakhs of people were getting impacted. Apart from people getting impacted, loss of life was very high decades ago. Now, decades of 2000 and decades of 22, they are different. 2020, they are different. Loss of life is already minimized. So what is now is happening is compounding, cascading effects, local impacts have become very, very strong, and then they are becoming beyond our coping capacity. So for that, we need to generate robust science and guidance for managing the disaster by anticipating the impacts, and then generate a guidance to the local administrators and the departments to minimize, plan a strategy to minimize the impacts by taking the focus and anticipating the impacts. So that's where our development also is contributing to that. Irregular, unplanned development, which is not guided by the changing vulnerabilities, and our own development is adding the risk to the lives of our people, properties. So our population density is so high. So what I am trying to do here is, I am trying to project what are the characteristics of rainfall changing at local level, what the present day products and analysis papers are suggesting that we have 10 different rainfall analysis. We have 10 different data sets globally available, some are locally available. We have our own rain gauge networks within the state of Telangana and Andhra Pradesh. So we are not using all that information available. So I am trying to present how the climate change triggered rainfall extremes are contributing to the changing characteristics of impacts and the risk landscape. So if you go to that, so in recent years, you can see flood has become more important than all other extremes, different extreme events in that particular matter. And then total affected people, if you see, affected people are more in terms of drought. So you have to see, understand both the things. So frequency of extreme events, floods are more happening, more frequently happening, but impact is more on the drought. So in terms of economic losses, it is pretty high in terms of tropical cyclones, we are in 5th position in terms of economic loss. So almost we have lost 57 million US dollars. So in terms of thunderstorms, we have lost almost 6 million US dollars. And then in terms of floods, we are third, 136 millions we have lost. So you can see the assets now. In the case of Vijayawada floods, you can see personal assets, lifelong earnings have lost, many people have lost. So now we have to generate a guidance to address this particular factor. So this is not working. Anyway, so this is another site, other Center for Science and Environment is doing. So what they are compiling is what all extreme events recorded and reported by IMD are compiled and put in a particular state. So for 2023, what they have found out is 318 days out of 365. Somewhere, some part of the country has recorded some extreme event. It could be heat wave, it could be anything. So you can see, and in terms of human loss, deaths, and see, we are generating the compound impact, comprehensive manner the impacts are doing. So based on our meteorological information, several organizations are working to generate so much information to plan and anticipate the impacts and prepare a response strategy, emergency response and risk management activity. So this is one of that exercise which countries have doing. You can see this particular plot. Daily things have been reported and tabulated online. It is online site, anybody can look at it. So monsoon is very important for us. So this is IMD's 0.25 degrees data. So mean from 71 to 2020 looks like this. We are very familiar with this. But the amount of precipitation, annual precipitation coming out of monsoon is substantial. We say that on an average 70%, but it varies spatially from one point to another point. And more importantly, the coefficient of variability. We know that less precipitation areas are having more variability. This is with IMD 0.25. This is with NCMRWF analysis, that IMD-AA it is called. So from 1979, current 2023, hourly parameters, 3-hourly parameters are available at 12 kilometer grid scale. Can you imagine reanalysis available at 12 kilometer resolution? Nobody in the world is producing it and generating it. So this is what, if you see, we all know about this pattern, but within this pattern, you can see the difference of variability when you come to 12 kilometers, how much variability is there, and variability characteristics are changing. So this is in recent 79 to 2022. So that's how it appears. So in terms of rainfall coming up to low rainfall, up to 64 mm. If you see IMD plot shows like this, but more importantly, IMD has generated this particular plot. So those are the points where red color are there. Rainfall is trend is increasing trend. So when you generate a forecast, and already our location has a tendency to receive more and more rainfall and ready to break the past records. That's what it conveys. So it is ready to break past records means when you are living in this region. So I am definitely pointing out in this region, Telangana and coastal Andhra, you can see. So densely increasing tendency is already captured and conveyed, but we are not making use of this information at all. Even in publications, we are not mentioning it. So this is for moderate precipitation from 65 mm to 115 mm. So here again you see our area is very characteristically showing that we are on the trend of breaking the past records very clearly. So this shows what impacts are going to be much higher than the past. So our response systems have to be totally different from the way we are dealing with the extremes on ground, working with our own departments, our own agencies who have to protect people and protect the properties, not only government properties, on individuals. So to plan that, we have already these evidences, not only the rainfall, even moderate rainfall up to 110 mm. So we have these tendencies available. And for higher temperatures, present data is not showing any, these are all IMD plots only, not much change is there. So another more important thing which I want to show. So global warming has started from 1980, where global industrialization started, and that's where the warming started changing the characteristics. So if you see decades of 81 to 90, these were the areas where heavy, very heavy, extremely heavy rainfall were happening at the district level. So when you come to next decade of 91 to 2000, how the landscape has changed. In 10 years, warming started producing different characteristics of rainfall altogether. So this is all available in going to next decade, 2000 to 2010, it is completely different. Are we making use of this information? So we have to see that we are on the tendency of breaking the records. Once you take into consideration, forecasts will have the value for anticipating higher and higher precipitation. So when you go to present decade of 2011 to 2020, on month wise you see June, July, August, September. So things are different. It is spread all over the country, but our areas are common, whether you see earlier ones and new ones. And this is the difference of present decade using IMDAA NCMRWF reanalysis 12 kilometer. Anomalies of 2012 to 2022. So this is the rainfall change that has happened from the previous 30 years of 82 to 21, and with reference to that change of the recent decade. You see how much increase. Northwest India precipitation is increasing, which Dr. Naik has told in his public talk in the first talk itself. So that is very much there. Why it is happening also I will briefly touch upon. And then that change is statistically significant. And here again you see we are at the thick of highest value of change. And similarly, this is about heavy rainfall days. We have seen the frequency of heavy rainfall earlier. Now heavy rainfall days are also statistically significant, that is happening. So we are living, particularly Telugu states are living in the most vulnerable, impacted, already getting impacted zone of climate change in terms of extreme rainfall. So this is for very heavy rainfall. Here we have this, but significance is not there. But some of the trends are started happening. Maybe next 10 years we will have this significance available. So you can clearly see short-lived wet extremes. This is over our area only, and over India, for example, appropriately for India. So short-lived high precipitation in the NCMRWF analysis, 12 kilometer analysis, very clear signal is available. We have hardly made use of that data, but this analysis is done by another agencies, NGOs. What diagrams are showing, some of the IMD diagrams, most of the diagrams which have fully exploited NCMRWF 12 kilometer data is CEEW, that is an NGO. They are working for the society, minimizing the risk of the people, mapping the risk of the people, using the information generated by us. Coming to Andhra Pradesh, we have seen earlier ones. This is by our own Andhra Pradesh network, which has got about 1900 automatic weather stations running from really 2006 onwards. Continuous data is available both for Andhra Pradesh and Telangana. Telangana has about 950 stations. Andhra has about 1800, 1900 stations. That's a very big number. So even that state data also shows that this is the total rainfall, and variability is higher in Rayalaseema segment, variability is less, high rainfall zone, variability is less. And then the trend is also significantly increasing in this area. not only NCMRWF data, IMD data, our own network managed, maintained by the state governments, very high resolution, 15 minutes sampling data is also showing that. Frequency of rainy days are also high. So there are so much of information we are not making use of it. I am just flagging here, so much is available. So our students have so much information to bring out much more detailed information at district level, sub-district level to manage. District atlases have to be prepared. That could be a project of our MSc students and MTech students. So for their own districts, if they do, they will be happy to see that. This is about Telangana. It is also showing, you can see eastern Telangana, where we have seen rainfall happening here has brought havoc to Vijayawada and Eluru districts. And these are the same increasing, decreasing trends which we have seen in IMD are shown by the data of our state networks also. So they are all converging now. Nobody need to question quality, whether that is good, this is not good, only IMD data is good. No. NGOs and other institutions have done and provided these maps in public domain just to convey that all are conveying the same signal, but with higher resolution, because data resolution is higher. So they are all confirming the same trend of extreme events, breaking their own records of the past year on year, and then we have to get ready for managing them. And if you go, this is again published this month only, multi-hazard, each block is impacted by different multiple extreme events. So impacts are compounded now. So sometime you will have cyclone, sometime you will have heat wave, sometime you will have flood. So you have a sequence of events impacting a particular region on and off. So that's how here cyclones means they have included all low pressure systems, right from low pressure area to cyclone. So in their own understanding, they are taken in terms of impact on the people. Whatever we call cyclonic circulation, they have taken it as a cyclone. So somebody of us have to work with them to make it more representative, more and more specific for action. So this is one particular sample which they have prepared. You can see all over India is impacted. 85% of the country is impacted by multiple hazards. So this is another one where variability of rainfall is high. In those areas, swapping of extremes are happening. Sometime experienced by flood, same area will experience by drought, and drought areas are experienced by flood. This they are calling as swapping of extremes between flood and drought. See, in their own wisdom, they are generating this information. We all know that variability is high means you will have wet spells and dry spells. Between the wet spells, longer dry spells will be there. Our science tells, but on ground we have not mapped it. So that is mapped by these people means you have to have extra risk management options in those areas where impacted by droughts and floods intermittently. So risk is impacted by, we only talk about these exposure. We don't go into other parameters for the risk management. Even generating this information, we are not going to a micro level analysis and assessment. And with forecast, which is already there, how impact would be there of an impending extreme event. So that's where we have to move in now. So we have to also take into information. Now GIS plots are available, public domain plots are available. So these will change sensitivity of extreme event, sensitivity of a location will change the impact. So this is, we have to, maps are available, you can know where you are upper level, where you are downstream, low-lying downstream, and other things. Local people all know, but district level you can assess and where the extreme rainfall is expected to happen in forecast, and in every 15 minutes you have a rainfall information available. When it has started, what was the rainfall intensity, duration of that high intensity. So you can always, using this information, assess at what time the runoff from the catchment area, source zone of extreme rainfall, downstream, when it will come, how much volume it will come. So those are all thumb rule calculations are there. We have to help to generate. Already those who are in these vulnerable areas, previous slide has mapped the risks already, existing risks. They will be changing. with the time, every year, every 2 years, because of landslides and new developments, mining will take place, so many other things are happening. So you have to have updating this information. So there are agencies who are updating that information, putting in public domain. So only we have to access them and to analyze changing landscape of risk and impacts that are going to be changing in time because of that. And more importantly, who have adaptive capacity. We know the domain of population, what kind of larger population, their economic levels, etc. So their adaptive capacity also we should assess. This, once you give this information, state governments are very smart with this information, so they can see where help is required, and on long term basis, risk reduction actions, where to start and plan, how much you have to plan the development activity, resilient development activity. So if you see, once this analysis done by CEW, again I am telling, Andhra is second high risk zone. So this we have to update and do it at sub-district level, panchayat level. Now information is available, so we have to do that. 12 kilometers from NCMRWF, and imagine Andhra has 1800 rainfall and automatic weather station. Telangana has about 950. So you can go to micro level of that variability characteristics and risk profile. And we talk about very frequently we talk about the thing, rainfall has decreased, we are having problem of river water availability, etc., etc. So what we have done between 2015 and 2018 is worked with NRSC, worked with CWC, and did a reassessment of water availability in different river basins of India. To the decades of 55 to 84, between the decades of 65 to 84, and between 85 to 2015. So that's where the global warming rainfall characteristics have been changing, which we have seen how the water availability in different river basins of India has changed. Whether it has changed, whether it significantly has changed, or we are unable to manage the resource which is made available by the monsoon rainfall and the river basin flows. So if you see, so this was the rainfall, and this many BCMs, billion cubic meters, was available up to decades of 65. Up to decades of 85, yes, some reduction has taken place, but it is less than 10%, 3945, 3853. But when the global warming started, subsequently it is increased to 3880. So that means rainfall started increasing, which you have seen earlier also. So that rainfall increase has almost come to the close, because this all done by with IMD's 0.25 degree daily rainfall analysis. But if you do with NCMRWF analysis, this updation will be different, I am sure. But this gives a signal that rainfall has not changed. It is less than 1 sigma variability in terms of BCM made available by various rivers, despite snow melting, despite all other problems of river management, dams, structures, whatever we have done and not done. You can clearly see from 55 decade to 85 decade, some decrease somewhere is there. You can different basins, increase is also there. So, but significantly, but if you take Krishna, nothing has changed. So you can Mahanadi, nothing has changed. Indus has increased because of melting. Godavari, little decrease is there. Godavari is here, no change in Godavari. India as a whole, highly non-significant change. From 85 to 2015, the same pattern, no significant turnaround of the volumes. Those characteristics have not changed at all, many river basins. So what it says is we have enough water and we are unable to manage it equitably and in a optimal distribution. So water management from the available water is important. So people talk that rainfall has decreased, we will have problems, we will become rivers become dry. So at least up to 2015 that has not happened. So this was a very important study which Planning Commission wanted to start before 2012, then we could start in 2015 and came out this study at 2018. This report is available online from the website of Central Water Commission.
Dr. Ramesh.
I'll close. So this warming is there. Warming we know after, After 1980 only steep warming has started. Impacts started prominent after 2000 when 1 degree warming has crossed. And last year Arctic, around Arctic warming was high. Antarctic only in the middle warming was high. So coming to this month, last August, whole of Antarctic is under warming anomaly, whole of Arctic is under warming anomaly. As we know that several publications are coming, they will have impact on our monsoon and other things. So these characteristics with the coupled model which NCMRWF is running, all other agencies including NCEP and everybody will run some from now onwards all coupled models. So you will get these characteristics incorporated in day-to-day assimilation. And in terms of temperature change, you can see in 2024 base itself started at 0.7. Earlier up to in 2023 it was different. So year to year so much change at global level is happening, local level is happening. So extreme landscape forecast. Why it is increasing, you are telling. See the loading of moisture loading right from 81 to 2010 anomaly. So much moisture loading is happening into monsoon atmosphere because of global warming. So that has to give extra precipitation, and this signal is there in IPCC reports. We have not taken note of it. And warming, moisture loading is seen from Redosan data and ERA 5 and as well as satellite data. All are showing the same signal. And annually, season-wise are done. You can see maximum loading is happening to this area. So Northwest India, Rajasthan, bound to Gujarat, bound to receive West Madhya Pradesh, bound to receive extreme precipitations, increasing with their trend. So this information is there. We have only published paper, we have not made use of it for practice. Science to practice we talk. So universities should bring this information, bring to the notice of through their projects, bring it to the news, quarterly news reports you release from the university, and conduct press conferences, alert the media, alert the government agencies to know about the changes that are happening. We are living in a high risk zone which is on the increasing trend. So these are all temperatures I just want to do. So last 2023 August was very disastrous month. So 95 days in 2023, 8 states, southern states were also impacted. You can see in that one particular month how much varied extremes have happened in the south, and the same year we had massive damage in Himachal Pradesh, particularly Uttar Pradesh and Himachal Pradesh by particularly in 115 days of that. But if you see June, July, August for this also north also for 2023 was a very devastating year. And in terms of temperatures, so this is where we have to see. Temperature anomaly in hill states is higher than rest of the world, rest of the country. So 1 degree means 7% increase in moisture, 12% increase in thunderstorm activity, lightning activity. Imagine 2.5% increase means cloud bursts, all those extreme rainfall events, epochs in the valleys are bound to happen. And if you see for August 2023 particularly, so anomaly, this is published every month by IMD website in Pune. And in terms of changing temperature 2 to 3 degrees, 2 to 5 degrees Himachal Pradesh, you can see these are our last year data. So once you have this kind of background information, when extremes start happening in August, so you can clearly say this is for Himachal Pradesh, this is for Kerala flooding we had. So we can know that we are already in the problem like this. So, we have to prepare much better way than the past. So, this is the recent monsoon depression and associated rainfall. Two epochs are there recently in this month only, end of last month and this month. That is how the systems have moved, and this is the extreme above normal rainfall so far in the country. So, we are one of those zones where flooding has been experienced and is experiencing currently. In this rainfall started flooding in West Bengal since yesterday because of rainfall happening 2 days earlier. So, this is important thing. We know that warming is more over Arabian Sea. That is because of ocean heat content increase significantly compared to Bay of Bengal. This is another reason for moisture loading and more precipitation, more warming, thunderstorms, etc., etc. And sea level rise is also responding. This is a seasonal sea level rise up to 2023. And 1 minute. I want to focus on this. This is very important. Recently, this week only, this paper is published by our friend Dev Niyogi from Texas, Austin. So, he has taken iMerge data for about 1056 global stations and then brought out very important thing. This is an urban area. When development is there, urban heat island bring the warming, but the rainfall also increases not only in the urban area, but downstream in the rural segments associated with that, wherever they are lying in downwind direction. So, these are the characteristics. So, he has given 4 metrics. So, this can be a simple direct straightaway project. One is computing urban annual precipitation anomaly, and another one is urban annual precipitation change anomaly. So, urban extreme precipitation magnitude anomaly. Here P95, P99, so R95, R95, R99, etc. So, this is frequency, precipitation frequency anomaly. So, these are the 4 metrics with iMerge data he has computed, and then if you see how much changes once autumn, winter, summer, spring. I request all the students to read this paper very. We have to, if you repeat this with available information, we can generate so much risk mapping over our state. So, what he has importantly brought out is there are zones where urban precipitation anomaly is positive, urban precipitation anomaly is negative also. So, this is the biggest anomaly globally. Everywhere that is not happening. So, if you see over India, particularly 50% areas are increasing the urban precipitation anomaly, 50% area are not increasing. So, continuously different areas have different values. So, we have to come to district level and sub-district level. So, then precipitation change anomaly, similarly our area has 69%, 39%, whereas only precipitation anomaly 50-50. When you go to precipitation change anomaly, it is changing is very high now, we have seen earlier. So, that quantification has done with the global data available. So, similarly there are other 2 metrics he has computed. So, when along with that we have the problem of aerosols, we have the problem of soil wetness when rainfall is happening more, and we have the problem of urban heat island effects. All the 3 impact differently, and that has been brought out very clearly. Apart from increase in rainfall here, downwind direction, 49 cities, more than 1 million precipitation, he has really quantified that increase downstream rural area as well. So, if you 1056 cities, how that's how with the height, if you go to Himalayas and hill states, so this is what will happen. With height, how rainfall UPA, positive to negative. So, most of the hilly zones it is positive. So much guiding information is already available, and we should make use of it. Another minute I will spend on the recent floods. What information we had? So, this is the forecast as suggested for the depression, which has given more rainfall in the coastal areas of Andhra and Telangana, and subsequent flooding. So, 5 days before, 3 days before, 2 days before, with the different color code, high risks, these are all given in the warnings. And at the same time, we have information, our own networks. So much Andhra network, so much Telangana network are showing, and this combined map, when extremes are happening back to back, Andhra data, Telangana data are shared, and these maps are analyzed. So we know the warning information, we know when this warning has started happening, and 15 minutes we have this kind of high density information. Then we should anticipate to see, and we have at the same time information online. Most of the reservoirs are already full, for example in Krishna catchment, and these subsystems which are coming and meeting in Krishna from Telangana, and all that information is simultaneously is there. By then everything is full, there is no storage. And in that situation, that has never happened in the past, and this is one thumb rule I am telling. 1 centimeter rainfall happening 1 square kilometer area, it will create about 1 million liters of water. So volume of water that can generate is also known. So more importantly, when releases are there from all sides to Prakasham barrage and coming from Muneru, Paleru, etc., so additional water coming in. So we have storages, but they were full. But by planning 4 days before, 5 days before, had we worked together and see how much buffer we have to create by release water 5 days before, 6 days before, then perhaps we could have possibilities of allowing this water coming into the Krishna itself through Budameru diversion channel could have become a possibility. I am just telling, I don't know whether it happen or not, possible not happen. But with all that real-time information, river value, river discharge and everything, we have not made effort to minimize the flooding possibilities. So we had to make effort of that. So this example I am showing, so much information locally is also generated, we are not making use of it, and then which way they are flowing. Once you have this information, whole city is between these two. This is coming from Prakasham barrage, this is coming from Budameru. So directly, it is not coming through diversion channel. So directly, so this has only led to the flooding. So was there a possibility to avoid this release had we made use of all the information available? That is a question we have to ask for ourselves. So if that is possible, we have to create a basis for that to happen. So that's where I am presenting this. And in terms of risk, regional 3 days before, India is put on third large risk country in the world, because number 1 and 2 are islands, Philippines and Indonesia. Highly populated country is third. So in many respects, we are there in that risk zone, vulnerable zone, and we have to make effort, and we have to work on good data. We are working on this. You see presentations, you will say that good observations, good decision making. Good decision making, we will have to make it to happen. So with so much of information, and train how to use that information. That is where our academics have to use all this information, how to make use of it. So we have to teach the administrators how to make use of this information, which is useful for everybody. So that's where our work lies here, train to use, and then good governance efforts are made, and private sector right investments are required, right mindset all the more, which is more important. And we have to protect this economic value of the development, economic value of our own individual assets, and which are contributing to not only the families, to the national GDP. Thank you very much.
Thank you for a wonderful presentation, Dr. Ramesh. Excellent information, how the data that we are generating can be used to save lives and property, and how to prepare for the better future. Quick comments?
I have a layman question.
Yes, sir.
In our country, the rural area is much, much higher than the urban area.
Yes.
But most of our observatories are located in the urban cities. Do you think there will be some bias in our measurements made in the urban areas?
That's not true anymore, at least in Telangana and Andhra Pradesh. They are all in taluk and sub-taluk level only. When 1800 automatic weather stations are there in state of Andhra Pradesh, they are all in rural areas only, not in cities. Cities are covered by already by many agencies, not only IMD, Agriculture Department, etc. So at least in our state of Andhra Pradesh, Telangana, Karnataka, Maharashtra, that is not true.
Thank you, sir. Thank you for your wonderful presentation.
Dr. Ramesh?
Yes, sir.
Yeah. fantastic,
let,
really
I think
totally new. I never imagined that I remember my professor, Professor Rokkan Ramanathan Garu, was telling me long time back, maybe 30, 40 years back, there are three types of research: new data, new observation, new results. That is fantastic. Old data, new result. That is your contribution. Fantastic. And you should send this article to a journal like Nature Climate Change. And really, it's not necessary to solve big models, big equations, nothing of that sort. We already have lot of new information in the data like simple rainfall. Such a fantastic, really, I learned a lot from you. Thank you very, very much.
Sir, I have not generated any information. I have only collated and trying to interpret.
But what you generated, new information, for me it is new.
Yes.
I learned a lot.
Thank
I
you,
think
sir.
for many people it is new.
Thank
I
you.
never thought in the old data there is so much new information.
New information.
That's what my professor Ramanathan Garu told me. So it is
Yeah, thank you.
fantastic.
Yeah.
You should send to a journal like Nature Climate Change. You should-
Purpose of presenting that is my own concern. All this available in public domain, we are just not making use of
Fantastic,
it.
fantastic. Really,
Doctor,
very, very good.
Thank you, sir.
Dr. KJ Ramesh Garu, first of all, please this side, sir. Here,
Sir.
this side.
Yes, sir.
I am from here.
yes.
I
Sorry.
would like to congratulate you,
Thank you.
for the type of information you have thrown during your presentation. Straight away I want to come to the point
Yes.
that Andhra and Telangana are going to face extreme rainfall events. And your data also what has shown for 50 years or more, also you were saying. But my doubt is whether the models are also have given this information or,
This NCMRWF analysis is generated by the model itself.
okay. And it is supported by data also.
Data also. That's why I am telling IMD data and this data I have side by side I have presented.
Yeah, yeah. Mostly the Kerala is also experiencing
Yes, yes.
a
Kerala
similar
also
thing.
is there. Kerala also I have shown, no? 2023.
So as you said, people should be the government and people should be more alert.
No, we have to make people
Yeah,
to
aware,
make
aware.
use of this information. That effort lies
No,
with the
that's-
academic departments and universities.
How do we take forward this for the society and public? That
Yes.
is very important.
Very important.
Yeah. Thank you for your.
Sir, a small question, sir. How is this pollution within the cities? The pollution has raised a lot. The suspended dust and industrial pollution and vehicular pollution has increased drastically. And how is this really controlling the monsoonal system? And is this the cause why you have the Antarctic and Arctic the highs in temperatures? do you
No,
think?
polar warming is by global change.
Yeah.
Because of carbon dioxide emissions, maximum emissions happening around Arctic, because most developed countries, Europe, America, Japan, Korea, around Arctic only. So their emissions were highest so far, and they are impacted more, and Arctic ice is melting more accelerated. Antarctic started happening because of natural warming responses. So from 23 to 24, how much change? Antarctica was never warming so far. Only the peripheral segments of Antarctica were warming anomaly. Now 2024 August showing whole of Antarctica continent also is on the warming anomaly zone. So that is our global changes. Those impacts will change monsoon. Already papers are coming. Global warming will increase the monsoon rainfall, whereas Antarctic polar warming will decrease the monsoon rainfall. Only papers started coming with models. We will have to see what new guidance comes from IPCC 7th cycle assessment to that effect. And IPCC is coming out with a special report on urban areas. They are already working on it as a part of AR7 cycle. So this paper which I have presented now, that has taken account of urban heat island effects, where pollution and local transport emissions, industrial emissions, and different characteristics of aerosols, absorbing, non-absorbing, carbonaceous, non-carbonaceous, all those are taken note of. And IPCC report coming maybe in 2 years' time will throw much more guidance material for urban areas. So this paper is a eye-opening paper, PNAS, just appeared last week. Fantastic work by our Dev's group. Thank you.
Thank you so much,
Dr.
sir.
Ramesh.
It's
I
a-
think, let's move on. Thank you again for an excellent presentation. So we will move to the next section where we have 4 invited talks. The first one will be by Dr. Gnanaseelan from IITM Pune. I've known him for a long time, also through my association at Florida State with him. So he will be talking about decadal prediction of Indian summer monsoon. You have 15 minutes for presentation, Gnanaseelan.
Thank you, Vijay. Good morning, everyone. I'm not an alumni of Andhra University, but I benefited from Andhra University through the guidance from Professor T.N. Krishnamurthy at FSU. So I am also a beneficiary. Today I will be talking about the decadal prediction of Indian summer monsoon, mainly the decadal prediction efforts of India and IITM. And mainly it's an effort of IITM, the Climate Variability and Prediction Group, and NCMRWF and MOES. And our group is about 30 scientists, and we provide opportunities for many students across all the universities, including Andhra University. And we have been working on these topics. One major activity is the Earth system model development, and the monsoon teleconnections in the decadal time scale, which we know very little, and the interaction between the different climate modes, which is also not well explored, which is being studied at IITM now. And as part of a deep ocean mission, we are also working on the projections of tropical cyclones, especially over the North Indian Ocean. And we have to provide the decadal climate prediction for the next 1 to 10 years. And we also need to develop decadal climate prediction products for different applications, such as agriculture, the hydrology or energy sectors. And as we have been seeing in the last 3 days, there is a lot of emphasis on the climate extremes. So we are also working on the climate extremes, its understanding and its predictability, and even the decadal prediction. And then many of the climate processes are not known. So we are working on understanding the climate processes using the IITM decadal prediction system. And we are also, there's a group on hydroclimate studies. And if you look at the interannual variations of Indian summer monsoon, so you can see the green ones are the excess monsoon years and the red ones are the deficit years. You can see there's a significant interannual variability. But what you can see in an overall over 150 years or so, you don't see any unstable behavior. Monsoon is more or less stable. But if you look at the 31-year running mean, see there is a clear multi-decadal variability which is significant, which is present. So this multi-decadal variability has been examined by some other studies, but there's a big gap lies in this. If you simply decompose the Indian monsoon time series, you see it is dominated by the interannual variabilities. So this is the first one. It's a biennial variability, the variability in 2-year time scale, and then followed by the variability at 7-year period, which is mostly forced by ENSO. And then there are decadal variabilities at 10 years, 25 years, and 60 years. So when you see this the 60-year period, so which explains about 10% of variability, so which is very important. So now if you look at that 60-year cycle, and if you regress the IMF5 to the global sea surface temperature, you can see there are many pockets of oceans like Indian Ocean, the El Nino region, and the PDO region, the North Pacific, and the North Atlantic. They all are very significantly related to the Indian monsoon in the decadal time scale. So now this is the Atlantic multi-decadal variability. You can see there are periods of cooling in the North Atlantic, and there is a period of warming, and this has a periodicity of 60 to 70 years. And similarly, you can see the Pacific decadal variability, the period of the horseshoe warming pattern in the north and south, followed by a cooling in the western central Pacific. So this has a periodicity of 20 years. So they all contribute to the climate variability over especially the decadal and multi-decadal variability of the climate. And if you regress the Atlantic multi-decadal variability over the rainfall patterns over the globe, you can see they are significantly positively correlated with Indian rainfall. And if you see the vertical velocities are the surface winds, you can see there they can induce what changes, warming or cooling happening in the North Atlantic, which has very strong impact on the upward motion or the convection over the Western Pacific and Indian region, and subsidence over the Central Pacific region during its positive phase or when the North Atlantic warms. So this can induce large impact on the Indian monsoon, and it also has, we were discussing about the circulations in the Northwest Pacific and the North Pacific. So they can also impact this, and you can also see the tropospheric temperature. So there's a large warming of about 2 to 3 degrees centigrade in the Asian landmass during the positive phase of the AMO and cooling in the negative phase of AMO. So this warming changes the thermal gradient between the land and the ocean, so which can induce or which can favor more rainfall through the increased cross-equatorial flow. So they all can impact the monsoon in the interannual time scale, in the decadal time scale. So now if you look at this, what you see is in the recent years, for example, so these relationships are changing. So that's a concern for the forecasting agencies, because the modes of variabilities and their relationships are changing. For example, in the recent years, if you see, the relationship, this is a positive AMO relationship with the Indian monsoon, but this is the recent years. It's also a positive phase of our AMO, but the relationship has in fact reversed. So that's an important open question, why such changes are happening. So one possible mechanism is, if you see the recent years, it is characterized by large warming in the Indian Ocean. So the warming in the Indian Ocean can weaken then the north-south temperature gradient, which can change the monsoon flow and the monsoon. So that is one possible the impact. So these are all open questions. So we need to understand in the decadal timescales. And see, another important component of the multi-decadal variability is, like during the positive phase, if you look at the composites of daily rainfall, and these are the blue ones are rainfall, and the red ones are the vorticity in the North Atlantic. You see, the important thing what you can notice is the positive rainfall, they all happens during the the positive AMO years as clusters. So, and similarly, the negative rainfall, see, like you can see the rainfall, negative rainfall, blue is rainfall. So they all happens in a cluster during the AMO positive phase and negative phases. So this also strongly suggests, that its relevance, its importance to the monsoon decadal variability. And coming back to the development of decadal climate prediction, this topic is relatively new because we are all familiar with the weather prediction and extended range and up to the seasonal prediction. So these are familiar to this audience, and we are also familiar with the climate projections. But there's a big gap between the seasonal prediction and the climate projection, that is the prediction at annual to decadal timescales. So this is a big gap, which is what is now addressed by our group. And if you look at the annual to decadal timescale, the events, so they are all affected by many things. Like, it can be affected by the tropical tropospheric changes, the stratospheric changes, or even the El Nino southern oscillation to some extent. And it is mostly affected by the Pacific and Atlantic multi-decadal and decadal oscillations. It can also be influenced or controlled by the natural external forcing. So this is a very complicated thing to forecast because it is influenced by many things, unlike the other timescales. So now if you look at the predictability from the initial state of a model, you can see, the initial state of a model can impact the forecast for some years. So they may be impacting heavily in the first year, and then they drastically come down, and maybe at some period, 6 to 10 years, so they come down. But at the same time, if you look at the external forcing, like anthropogenic forcing, and you can see, and they, in the first few years, they are not very important, but maybe in the decadal time scale onwards. So they are also important. So that is why making this prediction very, very complex. And now if you look at another one, see, it is a subseasonal to seasonal time scale. It is demonstrated very well that the ensemble members, so if you have ensemble members, so it can reduce the uncertainties of initial conditions, and it can provide a better forecast, better skillful forecast. But similarly, if you look at the seasonal to decadal forecast, so you can see the number of ensembles play a very important role. For example, you need to have at least 10 members to have good decadal prediction system, which in fact the controls the prediction capability because it requires massive computational facility. And the first question is whether the decadal prediction make any sense. Can you predict? Because the predicting weather in few hours itself is very complex, but how can you predict all these few years ahead? So now, important experiment they have done with the UKMO model. So they came out with, very thrilling results. You can see this panel is the skill of the predicting the surface temperature 2 to 5 years ahead. And this is the prediction of surface temperature a season ahead. So you can very well see that the predicting the surface temperature 2 to 5 years ahead has better skill than the predicting surface temperature before a season. So that's the important thing. How can you get that? So now you can see, but if you see the skill of seasonal prediction, that is very good in the tropics. But if you see the extra tropics, and the skill in even predicting seasonal time scale is very bad. So now this opens up a big challenge. So the decadal prediction is possible or not possible. So now coming back to the rainfall predictions. This is the surface temperature prediction. And if you come to the the rainfall prediction, said the skill is very bad. So the seasonal prediction has at least some skill, but if you see the decadal prediction skill, they are very bad. So that is a challenge. See, again, it's an open challenge for the decadal prediction. But now, so looking at that, the skill, the WMO came out with, establishing a new center in 2017, a lead center for annual to decadal climate prediction. So these are the centers participating in, the global centers participating in this effort. The forecast from all the centers are used to prepare the global annual to decadal climate update, which is available here. And now IITM India is also participating as one member in this effort.
Dr. Seal, 2 minutes.
And these are the prediction. Okay. So these are the prediction for 2024 surface temperature. So you can see it's prediction made in 2023. And this is for the next 5 years. So you can see all the models, ensemble mean, and this is the IITM model, what it shows. And all the models are showing, high, the warm conditions for the next 5 years. And this is the prediction for the rainfall. And you can see what the IITM model has predicted last year. So which is, you can see with the current forecast, it is coming out to be, very good for 2020, this year. And you can also see that the El Nino prediction, so it's showing La Nina, and the IITM model is also showing La Nina. And you can see the prediction of rainfall over the SARS-CoV region, which is very important for the South Asian countries. So which is showing, the positive rainfall anomalies is above mean. And you can see what the IITM model. And you can also see the time series prediction for the next 5 years. You can see it's an alarming, it's a global, the surface temperature can go up by 0.5 to 0.7 degrees centigrade, and it's shown in our model. And you can also see the different decadal variabilities, the PDVs, it's all going in the negative phase. This is what our model is showing. And you can also see, so this is the model we have used. You need an Earth system model. It has to be initialized. So the atmospheric ICs are basically the ensemble Kahneman filter based ensemble members prepared by NCMRWF, and the ocean ICs are prepared at IITM. And so these are the improvement from the model which has participated in CMIP 6. So how much this Earth system model we have improved. This is the improvement in the annual cycle, and this is the relation between the monsoon rainfall and the different climate indices based on the winds or the both dynamic and thermodynamic indices. So which are very well captured by our model. And this is a picture. It's a EOF of geopotential height, which is it is showing that North Atlantic oscillation. So you can see one is observation and one is model. You can see they're very well captured by our model. And this is the AMO index, which is the blue line overlaid with the 60-year cycle, so which is also captured very well. And this is the observed ENSO anomaly in the observation, and this is the simulated, the model ENSO. You can see the coherence, and this is the La Nina, and this is the response of rainfall to El Nino in the observation, and this is in the model, and this is the response of rainfall to La Nina, and this is the model. And you can see this is this heat map. It's a skill, with all the CMIP 6 models comparing with the IITM decadal prediction model. So you can see the bottom one is the observed. The skill, the variance score is here, and this is the IITM DCP. You can see, you can compare with all the other models, and this model is kept doing very well for this is ISMR. This is for NINO 3.4. This is PDO, and this is AMO. And it also captures all the not only decadal variability, the interannual variability. If you see the first mode, which is explaining the basin-wide warming or cooling, so which is captured. This is the observation and this is a model. And this is the observed second mode, which is the IOD. And this is the second mode in the model, which is captured well. And this is, again, the regressed field, so they are captured well. And another important deficiency of all the climate models is it's a the response of El Nino to the monsoon in all the models respond very hugely on the ENSO. So this is the observed relationship. So which is the black line, which is about 0.4, 0.5. But all the models shows about 0.8. But this model, the response comes out to be very realistic. And these are the global indices, the global temperature, the NINO3, the tropical Indian Ocean. See, the tropical Indian Ocean SST, the skill is about 0.7. So that is a very good thing. And IPO, then the IOD index, CMO index. The skill is very good in the model. And this is the temperature, sea surface temperature predicted for the year 2024. You can see the model predicted La Nina conditions for 2024. And this is the rainfall predicted for this year. And this is the rainfall. You can see, what you saw, the deficiency in the Gangetic plain, the model predicted very well. And in addition to the decadal and interannual predictions, so we also looked at how this model, whether the model has any skill in getting the extremes. So now you see that the model, the model skill in getting the extremes is like 0.53, whereas the other model skills can also be seen. Other models which has participated in the prediction. So you can see the skill is very good in our model. And with the bias correction, this this 0.5 skill can be improved to 0.6. And you can see that the different the extremes, large area, medium area, and small area extremes predicted for 2024. And see so there was some question, how the extremes are going to be in the next few years. So this is, from our model, what we can see is the next 5 years, next 10 years. So the next 10 years, the extreme can be, about multifold, like, about 2 to 3 times of the current. So this is like, the current status, 24, this is 24 to 28, and this is the 2024 to 33. So the extremes can be a real cause of concern for the next few years. So we need to be prepared. And with this, this is a summary. I'm not reading. And thank you very much. Thank you very much for giving me the opportunity.
Thank you, Seelan. Wonderful presentation. Appreciate all the work that you're doing with the decadal predictions. And kudos to the IITM for developing such capability and producing it for the world.
Thank you. I want to mention here that, my couple model work started with the guidance of Professor T. N. Krishnamurthy at FSU. So that really changed my career, my profile a lot. Thank you.
Anyway, thank you very much, Dr. Johnson. Wonderful talk. But I have a very fundamental question. Why decade? First of all, we know 24 hours diurnal okay, and astronomical yearly. But why 10 years? Decade? Why?
Yeah. See, that's a good question, but that is
because everybody is doing
See, people have some answers for multi-decadal. But why decadal? It could be due to the interaction between different multi-decadal modes. So, for example, now if you look at the different unknown areas, for example, the Indian Ocean SST. The Indian Ocean SST is showing a decadal variability. And the equatorial Indian Ocean winds are also showing a decadal variability. Probably, there is the interaction between the climate modes, which may be triggering, the decadal time scale variability. So, but this is still an open question, so which is not completely known, understood.
Yeah, because I have seen everybody is doing decadal. Daily, annual I understand, but why decade? And one more comment, not a question. The model by definition is an approximation to reality. In the words of Professor Lawrence, for the Navier-Stokes equations, complete equations, any model, whatever it is, however close you go to nature, it is always an approximation. So, we always expect, in principle, erroneous results. Maybe 0.001, but still it is an error. Okay? So, by model, by definition, the word model means it is an approximation to the reality. Thank you.
Yeah. So I totally agree with you, and that is true. But now with we see a lot of improvement in weather prediction and a shorter time scale prediction, mainly because we have more and more reliable observations now, and which are all assimilated in the models, and the models have shown tremendous improvement in the skill. But in a decadal prediction, for example, so the initial conditions of ocean, sea ice, the land, all those things are going to play a very important role. So once these are all initialized properly, so the skill of the model will still improve. So that way, along with the external forcing, so the skill of decadal predictions are going to be improved in the near future. Yeah. Thank you for that.
Thank you, Dr. Seelan. Let's invite the next speaker, Dr. T. Narayan Rao from NARL. We'll be talking about the spaceborne radars and future prospects. 15 minutes, if you can.
Pardon?
Okay. Okay. Good morning. First of all, actually, I am the alumni of this university, but not from that department. Actually, I did my master's in physics. So that way, but then I am very close to this department because presently I am doing research on meteorology. First of all, let me thank the organizers for inviting me to give this talk, and also I want to congratulate them for completing 75 years of excellence in teaching and research, and then also producing excellent researchers. So my presentation today is completely different from what you have been hearing for the last 2 days. So I'm going to talk about the spaceborne radars and how they are useful to study meteorology. Particularly, I'm going to talk about the precipitation radars. So these spaceborne radars have started nearly 2.5 decades back, and then these radars have produced wonderful science, and then also so many publications came out of this data. So I'm going to just show some of those things that what we have done, and then also elsewhere. But I'll not be able to show everything, but few results I will show. So this is the outline of my presentation. So first I will talk about then why these spaceborne radars are required. Then basically we will see these radars are basically used to identify different types of systems, precipitating systems, and then this being a radar, so you will get the vertical structure of precipitation. So you will get the morphology of the precipitation basically, and then these radars are actually used as a reference to generate the multi-satellite precipitation estimates, and then this is extensively used in the modeling for validation and also for the initialization of the models. So this, what are the problems in this, and then how people overcome, and then generated than now presently whatever we are getting. So, and then some of these radars are also used to understand, basically use it to get the microphysics of precipitation. So, those things also I will show some results, and then what is the future prospects of these radars. So, this is what we know from the ground gauge data. So, there's large spatial variability governed by a variety of processes, by topography, by the large scale synoptic systems. And then this is the seasonal variation, and these things are known from the rain gauge data and then ground based radars. But what we are missing here is actually the vertical structure of precipitation, and I'll show in the next slide why it is important. And also different types of rain, and then microphysics, and then over the open oceans also we don't get this information. So for all these things actually we need some space-bound radars. So if you see a mesoscale convective system, it will contain deep convective systems and also stratiform rain, covering vast regions. And then if you see the latent heating structure for the convective rain and stratiform rain, it's completely different. So we need to identify what kind of system it is, whether it's a stratiform rain or a convective rain, to realistically get the latent heating structure. And also to improve the ground-based radar estimation, also we need to segregate the stratiform and convective rain. And so for many practical purposes, actually we need to segregate the data into or to segregate the system, what kind of how much portion is the convective and how much portion is the stratiform rain. So to understand all these things, actually in 1997 they have launched one satellite called TRMM, Tropical Rainfall Measuring Mission. It's a US-Japan collaboration project. So this is the first space-borne radar in the first space-borne radar. So it operates at 13.8 gigahertz, and then initially it was at 350 kilometer, and it operated. They operated for 3 years, and then they found that it is a very potential tool. So and then they slightly raised the height, and then so it produced wonderful signs. And then the life of the satellite also increased when they lifted from 350 kilometer to 400 kilometer. So then it functioned nearly up to 2015. And then as a follow-up project, then they launched another satellite called GPM. It's called Global Precipitation Mission. So what it did is actually it has extended the capabilities of TRMM, both in terms of its capabilities. For example, TRMM is only having 13.8 gigahertz radar, is a Ku band radar, whereas GPM is having two radars. So one is one a Ku band radar, other one is a Ka band radar. So the Ka band radar is more sensitive, is also sensitive to snow and as a light rain. So and then also that is one way. So you can see different types of rain, and also the inclination angle is 65 degrees. So they can get data up to 67 degree north. Okay. So whereas the TRMM is mostly the tropical, it is covering only the subtropical, tropical and subtropical regions, whereas GPM covers much larger latitudinal extent. Okay. So these are the statistics, unique statistics actually they found. Actually it's a reviews of geophysics paper by House. And you can see very clearly the regions where the rainfall is high, and where the rainfall is actually the rain rates are small. And then you can see the equator in the December, January, February, slightly moving to the south of the equator. This ITCZ you can see it is moving to the south of the equator, and whereas in the June, July, August it is moving to the north of the equator, and very clearly see the migration of the ITCZ. And then some other features, known features, but then it is very clearly shown by this TRM data. And then you can also see where in the world where you have deep convective storms. You can see here, and then particularly in June, July, August, and particularly in this region, you see the deep convective storms, and then near the ITCZ. So several important features. I'm not going to tell all the things, but then you can see very clearly where the deep convective storms or where the wide convective storms. All these things we can get from this data. So coming back to the India, and we have done this actually segregation of all the data. We have gathered several years of data, and then we divided into the convective, stratiform, and then shallow rain, all the data. Then we can see the regions where the convection is dominant, where the stratiform rain is dominant. And then if you see one of the very clearly, we can see in the Arabian Sea and then West Coast, most of the rain, even the West Coast gets a lot of rain, but this most of the rain is a shallow rain. It's not a deep system. And then similarly, then you can see that if you not only the precipitation, you can also divide the precipitating systems into a deep convective core and then deep wide convective core, into different stratiform region and then shallow region. So then we can clearly see that the regions where these kind of precipitating systems are dominant in this region. Obviously, we can expect that in this region, you have the synoptic disturbances like in the monsoon season, you will have these low pressure systems and depressions. They will have a lot of stratiform regions. So these are big systems, mesoscale convective systems, and then you can see that's why you get a lot of stratiform rain is part of embedded in those kind of systems. And then as we have seen here, then you can see these isolated convective cores here, mostly in the Arabian Sea and then Western coast. And if you see the vertical structure, if you divide into different regions, in different climatic regions, Arabian Sea, Bay of Bengal, Northwest India, foothills of Himalayas, Central India, and Southeast Peninsular India. And the vertical structure itself is completely different, because this is actually a combination of nearly several years of data. We have plotted like a normalized frequency distribution. You can see in the Arabian Sea, mostly you see a shallow rain, just like we have seen in the other slide. And then in the Northwest India, most of the rain is in convective rain. And then you don't see this kind of the bright band structure, which is seen in the other regions. But whereas here you see mostly the convective rain is dominant here. Whereas in these regions, you see this kind of a bright band structure. Bright band is actually enhancement in the radar reflectivity near the 0 degree that we can see here. And then in the Northwest India also, you can see these reflectivity lines. If ISO lines, if you see, they are actually decreasing as you come down. So that clearly indicates there's a lot of evaporation of the drops is happening in that region. That's why actually these ISO lines are decreasing, because the reflectivity is actually is proportional to 6 power of the drop size. If the drop size reduces, then the reflectivity also reduces. So from these, actually we can infer what kind of microphysical process occurring in different climatic regimes. And if you want to understand actually what is happening in active and break spells, the monsoon, and then you know that active break spells are divided, are identified based on the rainfall, and then some people used some dynamical parameters, winds and other things. And then whatever you use, if you identify the active break spell, these are all the break spells defined by different people, and you don't get rain here as we expect, but you get a lot of rain in this region and then on the foothills of Himalayas, because during the break spell, the monsoon trough moves close to the foothills, so you get a lot of rain, but also in this region also we get a lot of rain. So we thought that instead of using that way, so we will actually define active and break spells for small regions using the same method, but for a small region we will identify, and then for those things actually we will study how the morphology of the precipitation. So in another paper we have divided the whole region into 26 coherent rainfall zones, and then for these regions we identified the active and break spells, or we call it the wet and dry spells. And then if you see the differences in the vertical structure in the active and break spells, mostly the break spell, actually the systems what we found is very shallow in nature, and whereas in active spell the systems are very deep. And then the difference is clearly shown here between these active and break spells. I think these systems are, in the active spell you have a positive anomaly, this is indicating that these systems are very deep, and whereas in the break spell the systems are shallow. And if you see the diurnal variation also of the rainfall is completely different. In these spells, normally we expect in the active spell we see mostly the evening time rainfall, but there are large spatial variability here in the diurnal variation also of rainfall also. And you see mostly this is actually the evening time. The time is shown here. The arrow indicates at what time it is peaking, rainfall is peaking. And then in the near the foothills, you see the rainfall is actually in the other direction. But in this region also, you see a midnight rainfall. And then this midnight rainfall, I will show later why it is happening in the midnight rainfall. But normally in the rain shadow region, we expect an evening time peak because of the insolation, but then we get a different type of peak in the diurnal variation. Pardon? Okay. So similarly, we are seeing in the break spell also, and then we try to understand what is happening in these regions, why the diurnal variation is like this. Particularly in this region, we see a lot of the convergence between the synoptic flow and then there's a downward side, and then in the open ocean, normally we expect in the early morning peak. So some of these things are actually, we try to understand why the diurnal variation is different in different regions. And then actually, as I told before, that these multi-satellite precipitation estimates, there are so many multi-satellite precipitation estimates are available now, like CMORPH, then TRMM, TMPA, hydro estimator, and several things. So what they do is, because they know that the infrared-based estimates having some problem and microwave passive systems are having some problem, so they try to combine the strengths of these things and then produce a better rainfall estimate. So, but then they combine in a different ways. Some people use ANN techniques, some people use simply morphing techniques. So different ways they combine the data and then produce multi-satellite precipitation estimates. And then whatever multi-satellite precipitation estimate, when you compared with the surface rain gauge data, what we found is actually all these estimates. So we can see here different multi-satellite precipitation estimates. All are actually underestimating along in the west coast, and then all are overestimating in this region and in this region. And then we try to understand actually why this is happening. And then with the TRM, actually we know these statistics I have shown earlier. What we found is actually most of these satellite products, particularly the IR-based estimates like geostationary satellite estimates, so they depend mostly on the cloud top temperature. So, and then in this region, you see a lot of virga rain in this region. Because of that, the IR is overestimating the rainfall. It is thinking that rainfall is there, but then it is not reaching the ground. And then particularly here in this region, predominantly the shallow rain is dominant here in this region. So, and then IR estimate actually, it want a deep, if you want more rain, the system should be deep. Okay, so but then whereas we are seeing here a shallow rain, so that is also wrongly estimating. Even the microwave estimates are also, passive microwave systems are also, they depend mostly on the ice scattering. And then since this is a shallow system, it is not having enough ice, so it's not producing the correct estimate. Okay, so and then this actually later, now the present version whatever we are having, so there actually they have changed so many things, particularly addressing the orographic rain and the shallow rain. So the later versions actually they corrected also many of these things, but still some problem persists in the data. So but then this data is very useful in addressing several problems. For example, I have shown that then we get in our region, like Gadanki is here, and then surrounding we have several automatic weather stations, we have several rain gauges. All are showing in the midnight rain, where we expect, actually it's a rain shadow region, so we expect a evening peak, but we are getting midnight peak. What we found is, from these multi-satellite precipitation estimates, there is systems are propagating in this direction. This is in all the active spells, the monsoon, and then you can see everywhere it's propagating all these systems, and then by the time they reach in this region, it is actually in the midnight. Okay, so these kind of propagating systems are predominant in the active monsoon side, active monsoon period, whereas in the break monsoon period, we don't see such kind of systems, and then we tried to understand why this propagation is happening only during the active monsoon spell. Okay, and then we tried to see that actually how much these cyclones are contributing to the annual and seasonal rainfall. I think because he has already given a signal, so I'm just skipping some of the things. This I will show one one slide here, because in a cloud there are several processes are occurring. Okay, from the nucleation to the cloud drop to the raindrop growth, and then during the raindrop descent to the ground. So several processes, and then using this kind of GPM data, we will be able to understand what is happening, what kind of microphysical process is dominant. For example, when this product was released, first we wanted to check whether this product is correct or not, whatever they are giving is correct or not. Because at Gadangi, we know that the raindrop size shows predominant seasonal variation. Because you see in the southwest monsoon, you see the drop size is slightly bigger than the smaller northeast monsoon side. So, and this is a very, very prominent feature, and several papers are explaining this, why it is happening. And you see these dashed lines are all different years, and this is the average picture, and then you see in all the years this feature is present. So it is a significant feature, and but when they release it, the first version, the version 3, and then we don't see any such feature here in the GPM data. And then we informed them that this is not happening, and then we tried different simulations and then showed that why this is happening. And then later they have changed the algorithm itself. The total algorithm is now revamped, and then now they are using a different kind of algorithm to give the these parameters. And using that algorithm, then we try to understand actually different regions, how the drop size is changing as a function of rain rate. And then you can see that actually in different regions you see different drop sizes here. For the same rain rate, you see different drop size. Okay, so the total intensity will be same, but then the size will be different. Okay, so then why this is happening? Because of some microphysical process difference. So we try to understand the microphysical differences in different regions by using this information. Okay, so we have used several parameters, and then synthesis is shown here. And then we studied the seasonal variations and then intra-seasonal. I think and yesterday one of my colleagues presented about the intra-seasonal variation in the drop size and then why it is happening. And if you see the present and then future spaceborne radars, of course TRMM was launched, and then the life is also over, and then GPM is presently in orbit. Now there is a satellite they launched in RainCube. It's an experimental satellite. Now the EarthCare is also launched. RainCube is an experimental satellite. Its life is also over. Now what is there in future? In the future, all these international community is thinking about how to address, how to fill the gaps. What is not known? Because there are, from our these 2 radars experience, we know something, and there are still some existing gaps are there. How to fill those gaps? How to take advance our knowledge? So one thing which is missing from these things are actually we don't know at the nucleation stage. So the aerosol cloud interaction, that is one of the missing gaps. So they are trying to come up with a mission called SCCP. There's aerosol cloud convection precipitation. It is also having 2 radars and some other instruments to address this problem. And then as most of the models actually most parameterizations, they're basically they are mass flux based parameterization. So the convective mass flux, so that is one of the missing link that we don't have that information. So there is another satellite. It's not one satellite. It's a constellation of 3 satellites. It's called. It's no more called actually D-Train. It's called now. It's the INCUS mission. Okay. So it's a constellation of 3 satellites. Just in 2 minutes gap, they see the same region, and then from the differences in the reflectivity, they try to estimate what is the convective mass flux. Okay. So people are now going with this kind of constellations and then different kinds of missions, and they probably will provide more information about these things And just to summarize my presentation, so these radars have given nearly 26 years of tremendous data, and then it is providing new insights into the morphology of precipitation, and also they are providing the microphysics of precipitation, a lot of information on the microphysics of precipitation. And then now these radars, with combining this radar, actually radars are becoming like a benchmark, and then they are used to correct the other satellite precipitation estimates, and then we're making merging, and then it's providing a very consistent multi-satellite precipitation estimates. So they are becoming, people are initializing that data in the models, and also they are using it as to validate the model performance. I think yesterday and day before yesterday also I have seen several people are using iMerge and then TMPA data. And so for all those things, the radars are becoming the standard. So they correct all those things with the radar measurement. And also it is providing in the future also, they are actually coming up with several missions to address the science problems. Thank you.
Thank you, Dr. Narayan Rao. Wonderful presentation on the precipitation radars. There is also a commercial sector that's now showing a lot of interest, and the CubeSats, as you mentioned, will have these technologies made available for a lot of future research and improving the microphysics. Thank you again. Professor Bhaskar Rao.
Hello, nice presentation, sir. You have shown one image of where you compared two models, out of two algorithms in your slides. Regarding that, I have a question. Do you think because you have not, considered some model parameters, do you think the data was collapsing? And that's the reason.
Where? In which one you are referring? I don't know. I have not used any model. I have not compared anything.
You said you changed the algorithm completely.
Oh, the algorithm for the retrieval of DM.
Yes.
We have not changed anything. What we did is we have checked the operational algorithm product. We know that at one region there is a large seasonal variation is there, but they are not reproducing that large seasonal variation, which is a very prominent and it's a consistent feature. Every year the same feature is seen, but the satellite products are not showing the same feature. So then what we told is actually there is something wrong in the algorithm. Okay. So what earlier they were using a different type of algorithm, whatever I have shown there, but now they came up with a different algorithm. Okay, so they use a DMR relation with some adjustment factor. So that relation they are using, and that is now it is also not 100% correct, but still it is giving the feature whatever we are seeing. Okay, then that feature is not only at Gadanki, in the whole southeast peninsular India, at several locations we have seen everywhere the same feature is there, but satellite is not showing that feature.
Okay, thank you.
Thank you for the wonderful lecture. Since you said radar is able to measure the cumulus convection features at very good resolution, and many of the modelers generally parameterize the convection with a different hypothesis. Is it at what horizontal resolution the vertical mass flux is being available at this particular time, so that
this vertical mass flux actually over the land regions wherever the radars are there, ground-based radars, you can get that very easily. But now they are coming up with another constellation of satellites. 3 satellites will fly continuously. They will see the same region, okay, in 2 minutes gap, and then by seeing the growth or decay of the convection, the cloud. So they will try to estimate what is the mass flux, whether how much mass is going into the higher altitudes and all those things. So that mass flux estimations they are going to estimate. So this satellite is not orbiting. It will be launched in 2027.
At what resolution?
Horizontal resolution is around 1 kilometer, I think.
Okay, thank you again for a wonderful presentation. We will have a small change in the program. I know people are waiting for a tea break, and we will break for 15 minutes for tea and then resume this session for the last 2 talks by Ashrit and Satyaban. So let's get back here by 11:40, if you can. All right, if you can take your seats, we will get started with the invited talks. Please get in and take your seats. Okay, we will continue these invited talks. I have the pleasure to invite Dr. Raghavendra Ashrit, my close friend and colleague for a long time. We studied together MSc, MTech, and also continued research in Pune. I know he has a lot of stories to tell, obviously, but today he will be talking about extreme precipitation events, forecasting challenges. And you have 15 minutes.
Thank you. Good afternoon, everyone. Focus of my talk will be like the extreme precipitation events, the forecasting challenges. All along whatever we have been hearing, I'll be slightly talking away from that, how the forecasters have to deal with the kinds of tools that are available and what all kinds of value additions that we'll have to make, what are the types of challenges they face, and what all promises that we have, and to what extent the promises are justified with the available technologies and things like that. Just to put in perspective, I wish to acknowledge my colleagues, yeah, I work with in NCMRWF and the BIMSTEC Center for Weather and Climate. Both are located in Noida in our center. So we all remember very well, this is very much fresh in memory, although this has been more than a decade, that we had this Mumbai deluge where the rainfall of just 24 hours exceeded like all records, all even beyond the records if there were any events in the memory and things like that. This is very much relevant, but typically what is we fail to see is these are the kind of events that are out of the blue, sporadic events out of the blue. In a sense, this is very much well accepted that this is part of the monsoon system associated with well-known synoptic disturbance and things like that, but the end result is something once in a while, like never seen before kind of an event. And this is like a challenge to NWP models. They have very good skill, generally very good skill in predicting large-scale synoptic features associated with these disturbances. And it has been improving also in the last 1 decade or so with increased sophistication data assimilation techniques and increasing model resolution and all. There is tremendous improvement, but still some of these kind of events will still be a challenge. And precisely to predict the intensity and growth, development, and these different processes that we want to capture in the model, it's still, it's a big challenge. So that is where like, it's still even today, like it's a big challenge for NWP models to accurately predict in terms of location, in terms of intensity, duration, and things like that. Again, another one, similar one we had during December 2015. This is also very much fresh in memory. And again, it shouldn't be anything different because it is the northeast monsoon period for Chennai, and Chennai is nothing new to all the like tropical cyclones in the post-monsoon season. It has its share of heavy rainfall events, but something like this, combination of contributing factors, unexpected, leading to unprecedented kind of events. How do we predict them? Always we get criticized when events of this magnitude and kind happen. Combined together, they lead to complex results, end results. So again, the same issue, like with all the improvements and development, we still have intensity, prediction and all, like we always have either an under intensification or over intensification type of thing. And especially if it is associated with a track or cyclonic system, we still have either fast moving system or a slow moving system kind of biases. Models still carry a lot of biases which the forecasters have to grapple with. Yeah, that's just a background of how or like where do these extremes fit in. Like the well-known systems, we seem to have no problem, but these are once in a lifetime kind of an event, like with very high return periods and all. Like that becomes a challenge. Do we actually have a way to delineate with the common events and the extreme kind of events? Of course, we have something built into the IMD definitions like extremely heavy rainfall, but not truly, it doesn't capture the imagination in terms of the extreme that we want to discuss about. I'll briefly touch upon how we can understand an extreme event in terms of for the rainfall or temperature, whatever. But most of my talk will be focused on rainfall. And then like, yeah, if there are claims that like our models are improving and there is improved skill in predicting all heavy rainfalls of higher thresholds and things like that, but how do we do the verification? Do we have effective ways of quantifying the accuracy and performance of the models? I'll discuss some of the challenges and some of the prospects with some cases over Mumbai and Chennai region, and what could be the strategies when we want to deal with extreme rainfall events. I will also touch upon the use of ensemble products. We have an ensemble prediction system in NCMRWF, it's called NEPS. I take some examples from our ensemble prediction system and show like what could be the different ways of expressing and giving guidance for the forecasters to be able to isolate and identify an impending extreme rainfall event. Then subsequently, before closing, I'll just touch upon the types of challenges in terms of observations, forecasting and verification. And also, no talk is complete without touching upon the artificial intelligence and machine learning kind of this thing and the kind of hype that is created all around the world. I'll briefly touch upon some of the aspects and conclude my talk. Yeah, this is a very classical, like everybody can understand, like the extremes are something which can be found in the tails of the distribution for rainfall and temperature and things like that. On the other hand, like extremes we can understand in terms of maxima, minima, or purely in terms of absolute magnitudes, or the rarity in terms of the frequency, like very, very low frequency kind of an events, or just in some of the recent cases that it just leaves a mark in terms of severity and its impact. So like this is bit of a like a controversial kind of a thing, like even because of non-meteorological, non-weather and non-environmental conditions also, like the impacts could be very large and we tend to translate them as something very extreme or things like that. So even the most common type of storms can leave lasting impact because so many other sociological or other impacts. So there could be many different kinds of definitions. One, if we want to pick from some early studies, like it could be established that what represents an extreme one-day event is highly variable climate type existing across India. So it's also not uniform. We can't have one definition for the whole country. So it's completely variable. So typically how we can understand is, yes, they are very severe and they are very rare. This is out, and like something like unexpected and unprepared, and it is something like the societies and communities have been able to manage and cope for a long time. It's something which is beyond those thresholds that can constitute an extreme event. There could be identified in different ways, like also you can see that we need the forecasts which can capture high in terms of spatial and temporal resolution. They can only produce this. Now that is an expectation. We have invested a large amount of infrastructure and in building up the technologies and making advantages, but still for extreme events, that's expectation. All the forecasters and the stakeholders expect that we capture all the events and all the processes. And also in future, like the projections, future projections also point towards increasing trend in the extremes. That's another need. So there is no escaping that we need proper forecasting and direct or indirect way to communicate and identify and isolate such extreme events. Yeah, so the standard WMO definition gives, like, independent of the thresholds is, this is also documented, like for any location, if we can identify 90th, 95th and 95th percentiles of precipitation, they can constitute stable and reliable like threshold to identify an extreme event. So this becomes useful in terms of changing climatologies, whether the region is homogeneous terrain or different climatological aspects or the hilly terrain, anything. So any definition based on the percentiles will actually give a very, very useful kind of, so directly for the forecasters or any, for public it may not be like clearly easily making sense. Public or any other direct first responder and all, they'll be normally useful to like 10 centimeter, 20 centimeter, 50 centimeter, something they can understand. But something, anything expressed in terms of percentiles, definitely it will be difficult. So this is still, the definition is still targeted more towards the people with awareness and scientific community and things like that. So that is the standard definition. I'm quickly going ahead just to see, like, these are some of the modeling frameworks that we use at NCMRWF for the routine forecasting, and especially with more focus whenever we have this kind of heavy rainfall events, we just switch to like the high resolution 4 kilometer models and the ensemble systems. We also try to take guidance from this thing. Yeah, please point out if I am going very slow, Vijay. Yeah, this graphic is very familiar. We can clearly see this is the Mumbai rainfall, daily rainfall time series. Here you have large number of like more than like nearly 70 years of daily monsoon rainfall, and what stands tall here is the famous or infamous Mumbai deluge. So this is what the models have to grapple with. And see what we can clearly see here is rainfall exceeding the 99th percentile. Okay, everything is based on observations. Rainfall exceeding 99th percentile is also very common. It's like you have large number of cases. Okay, you still have large number of cases, and almost every season you have some of these events. And this is where the challenge lies. We have tried to see how and we have tried to pick up, because this was we have only one chance of this kind of an event. We really can't expect whether the models are able to predict or not. Of course, we can do some past cases and see, like, there are claims and counterclaims about whether that could be simulated. We'll just investigate the recent 10 years where we have a stable model framework and tried to see over the Mumbai region, and picked up some few years and tried to see how just the day one forecast I just picked up. On the left side we have the observations and the forecast, just to try to compare and see, just with the focus on the monsoon rainfall over Mumbai, just the Mumbai region. It looks very nice. Like, it looks like models are doing quite well, because many of these dips are nicely predicted, right? And the sharp events, like even the global model with like 18 kilometers or something earlier, and only after 2018 or so we have high resolution 12 kilometers. Even when we didn't have very high resolution, our model was able to predict rainfall events more than 200 meters. But if you take a closer look, we see a model has too many of such events, probably even when observations didn't have, right? So this is also a drawback. So models do have this thing tend to overdo such events, and that's where the challenge comes. Like, the forecasters will have dilemma of how to measure it. We need to quantify. So extremes have this problem of, like, we can't straight away quantify it. Like, if we just write standard metrics, if we see, like, beyond 20 millimeters or so, all your verification metrics taper down to meaningless, very small values, insignificant values. Graphically, if I say and claim that my forecast is able to do it and all, but if I want to quantify based on even large number of cases, but for higher thresholds, always the values of whatever verification metric I choose becomes very, very low. This is one big challenge. So there is this one particular metric specially designed for focusing on the extreme and rare kind of events. So it is just making use of the standard metrics like hit rate, false alarm and things like that, and applying the logarithmic transformations to be able to boost the, especially towards the towards the tails of the distribution. So typically, SEDI metric, it lasts from -1 to +1. 1 stands for the perfect forecast. And for this particular event, like we can come up with this kind of this thing. So slightly boosted up the values, especially for the higher thresholds. So that will give some meaningful values, not necessarily approaching 1. Obviously, we can't expect. Yeah. 2 more minutes? 5 minutes? Yeah, fine. I'll just rush through this one. So these are some of the kinds of metrics where we try to quantify with focus on extremes, so that this is also done at ECMWF, and we have also been doing it for the last several years, just to see. Normally all the monsoon daily forecast, everything is fine, but are we improving for the extremes like 90th percentile and things like that? That is what we have been. This is again another case of Chennai heavy rainfall event. This was the highest one, heaviest one that occurred. And yeah, we also have make use of the network of observations that is available. Some of the events which are not very evident in the large scale, like the satellite and merged products and all, they show up very much with the localized event and all things like that. So we also carry out with location specific, making use of the localized rainfall data, which probably are missed in the forecast. And these are all quantified and communicated. All this is done to gain credibility and confidence among the forecasters, so that NWP products, if at all they are improving, that should be recorded, documented, and forecasters should be able to gain some confidence in making use of it. Not just the metrics, but also in terms of the process, whether the types of instabilities are captured or not. And even for each of the events, individual event-based verification is also important, because when the extremes are very few, and once in a while we have to rely on this kind of event-based verification methods. Yeah, and also in addition to that, we also do further value addition. So this is one particular event, like where you have a completely isolated peak, like nothing before and nothing after, and only through different kinds of post-processing we should be able to capture some of these events. Yeah, this is a probabilistic forecast. We rely on probabilistic estimates. Like typically, when we come into many members are able to there, and some of the members are able to capture the kind of extreme event. This is exceeding 11 centimeters. This kind of even event. This is what is, and also the same can be expressed against the climatology. Climatological extremes will allow you to see whether my event is okay. It may be heavy, it may not be heavy, but is it exceeding breaching the climatological 90th percentile? This kind of translation of extremes is what's important. Here also we have tried to show over Uttarakhand region, when this particular event like exceeding 19 centimeters is also captured. Similarly over Kerala. So directly models may fail, but as a proxy, different kinds of translation of your model products will be able to allow you to isolate and express, and also see consistently at different lead times if we are able to produce the heavier amounts or that's also done. Different kinds of post processing is used. So just before I close, I'll just touch upon all this. We are trying to use the extreme value analysis and ensembles, bringing them together. I have a PhD student who is working on it and try to develop indices based on historical knowledge and clubbing with the ensembles. And since there is, I'll just skip some of these results from my student. Yeah, that's what, these are the challenges. There are challenges from observations and modeling and forecasting and all the aspects. Just to see, yeah, this is one important thing. Very often all these rare events are rejected as outliers, especially when we want to talk about AI/ML. So AI/ML techniques which do all the pre-processing before going for any modeling, they clearly reject and leave many of these events as outliers, and these events will remain outside like unseen data. And I really doubt if AI/ML techniques can predict unseen data. Of course, there are a lot of claims and there is a lot of promise, but it will still be a challenge if train all the AI/ML models using all these tall sticks, except this one, and then predict this one. I don't think it is possible. So I just close it with that note, and this is just the summary of what all I have discussed, and that just I have tried to map my journey from Department of Meteorology Oceanography to NCMRWF. Thank you.
Excellent talk, Raghu. Particularly, I appreciate your attention to evaluating for finding the accuracy of these forecasts and have the enough evidence to compare those extreme events. A wonderful talk again. Any questions, comments?
Thank you, sir, for the wonderful talk. I have a general question, especially towards the model. Most of the models predicts rainfall, but the rainfall is huge, mostly overestimating at least cloud resolving scales. Question is, why models always produce a lot of rainfall? And then follow-up question is, how one can fix the issue? Thank you.
Yeah, this is a challenge in the sense like we need convective parameterization, we need higher resolution to be able to capture all the processes, and also as a result, like you can't avoid this overestimation. So you have all the embedded features nicely resolved. So that is something like if you go to a coarser resolution model, you have better skill. Forecast skill metric, if you depend on, you will have better skill, but some of these isolated peaks and other things you will not be able to. So we are getting it at the cost of accuracy. Heavier amounts have come, but they have been more. Yeah. The only way to the second part of your question is only wherever we have like long records, it will be possible to estimate the biases, like simple techniques, even without having to go to AI/ML kind of techniques, like the very standard like QQ mapping based kind of techniques, and are good enough to bring down this kind of biases. That's what we have shown in some of our publications. Different empirical quantile mapping techniques, they are good enough. Yes, you need at least some few seasons wherein you can calibrate, use it, that is good enough. You can bring out large biases, you can come out, especially at, and also you have methods to have wherever you can bias correct only wherever it is required. For the required thresholds only you can do it. That way you can have a differential kind of bias correction.
Thank you.
Okay, let's thank again for a wonderful presentation. Oops, okay, let's go.
No, I just want to add, maybe it is dependent on the triggering mechanism of the convection. How the cloud gives the rain, inherently there is a triggering mechanism. Nobody checks that because models tend to give more rainfall depending on that particular property, I think you agree.
Yeah, yes, you're right. Probably in future, like there is already talk is going on about scale-aware convection, scale-aware parameterization. Probably they will have slightly better performance, yeah.
Great. All right, let's move on to the last but not the least invited talk for this session by Dr. Satyaban from IMD Pune, talking about ENSO impacts on Indian summer monsoon rainfall.
Good afternoon, everyone. It's always pleasure to be back at Department of Meteorology and Oceanography, Andhra University. And it is always special to present my talk in front of my teacher or my research guide, Professor D.V. Bhaskar Rao. Actually, although I left this department about 16 years ago after completion of my PhD, still I am feeling very close to this department, and also I am feeling all these faculty, teachers, and my friends, all the things as just my family members due to my close association with the most of my teachers and friends and the current faculty members as well. And although the Andhra University, just one more minute I will give it is a good chance for me to talk. Although we studied at Andhra University at the very beginning of our career, we could get a good exposure at the Department of Meteorology, especially really dedication effort from our teachers. For example, when I started my PhD at that time, many of the institute and university as well, there was no facilities of computing resources as well as the modeling capacities. But Andhra University is one of the university around 2004 and 5, we could have run at least in a small computer our MM5 models. And just due to that one, that laid a strong foundation for my career or many of our researchers during that time. So with this, I will start my talk on the, actually currently I am working on the, because IMD means mostly people talk about the weather forecasting, but I am mostly working currently with, as per my specializations from the last more than a decade on the climate. I am working on the climate monitoring and prediction group of the climate research and services of the India Meteorological Department, Pune, where our mostly the famous long range forecast has been carried out for the many decades from now. So this outline for this talk, I will briefly cover to highlight many important things where this ENSO and Indian summer monsoon rainfall, recent ENSO variability and ISMR, and just last year we had a El Nino and its relation with 2023 monsoon, and seasonal forecast of India Meteorological Department. I will try to briefly cover, and monsoon 2024 so far, and quick summary. So we know whenever we talk about the monsoon, we know this a nice schematic diagram of this the variability of Indian summer monsoon in a different time scale, whether it is a interannual time scale or interdecadal time scale, or in terms of climate change, it is impacted by various external drivers. Among these, we know closely, for example, we know that ENSO, one of the major climate driver, where I am going to focus now. Apart from that, most of the studies also focused on Equino, or it is the Indian Ocean Dipole, or Atlantic Nino, all these tropical climate modes. But at the same time, most of these climate drivers also interact each other, which makes very complex how this rainfall is going to behave in the upcoming season. For example, this is how the cycle you can tell. For example, there is a La Nina, means there is a strong Walker circulation that will stay strong monsoon winds that will lead to in the negative Indian Ocean Dipole and negative Indian Dipole can in the next season in the weak Pacific trend winds. And then that can lead to the El Nino and weak Walker circulation, and that can in the following monsoon season, it will be a weak monsoon season. So this is the how complex interaction with the climate drivers takes place, and unless those models correctly simulate or correctly capture this interaction, this model is face challenges to accurately forecast this monsoon. So as we saw, this ENSO is the major climate driver. It is makes easy whenever there is ENSO phenomena. We know that if there is a La Nina, India is going to experience normal to above normal rainfall. If it is the El Nino, India is going to below normal rainfall. That is what the ISMR monsoon relationship. So this is what the rainfall pattern also we can see. But what happened in the recent 10 years, we can see many times the scientific community, they also talked this as a ENSO decade. For example, last 10 years, we can see there is no single year left without El Nino or La Nina. For example, starting from the 2014, we can see there is one El Nino developed. It is a kind of a long-lived El Nino covering the 3 calendar years part of these things. But then is a short-lived La Nina in 2016 and 2017 and another La Nina, followed by a 2018-19 El Nino. And then there is a triple dip La Nina, because the La Nina period evolved actually for the long period, which is called as the triple dip La Nina for the 3 winters in this time. And currently, just recently we ended with a El Nino this season. And it is obvious that whenever there is a El Nino 2015 or again El Nino 2010, India received a slightly below normal rainfall, but all the La Nina, it is makes normal to above normal rainfall. So, for example, if we can, as expected, 2023 Indian summer monsoon rainfall, actually there was actually at that time, there was a El Nino, strong El Nino observed in the Pacific. At the same time, there is a one positive Indian Ocean dipole. So the El Nino actually is contributed to the actually 95%, is slightly below normal rainfall. But sometimes what a positive Indian dipole mode that helps to compensating the negative impact of El Nino. So that is what even though it is El Nino, there is a negative anomaly we can see different, but intensity is still all India average sometimes is make as a normal rainfall. But then what happened as in the India Meteorological Department for a operational forecasting, because most of the model at the beginning of 2023, most of the model indicated that there is a El Nino is going to develop. So for an analog forecast, we try to understand how many years such events are occurred. For example, model indicated positive IOD is going to develop, or El Nino is going to develop. In the last past decades, if similar case happened, what is the rainfall would be behave? That is what we can call sometimes as an analog forecast. So when we try to understand, we could see that during the last 4 to 5 decades, similar event only twice, because there is a too strong El Nino when there is a significant positive Indian Ocean dipole was also there. That is what when the 1997, 2015, those two El Nino event also is known as the super El Nino. So, but what happened, again it makes complex. There is El Nino, there is a positive IOD, but what happened, there is a rainfall differences also there. That means there is a no similar rainfall pattern observed. In 1997, we know it is one of the strongest El Nino on the record, but still, although there is a negative rainfall anomaly in parts of India, the all India rainfall was 100%. But in the 2015 deficient rainfall, it was it is one of the deficient monsoon year, what is 86%. So then, apart from El Nino and positive IOD, some other things are driving such differences of rainfall. For example, what happened in the we know actually MJO also one of the major tropical climate drivers that is influencing Indian summer monsoon in the intra-seasonal scale, and in total that is contributing the seasonal total of the rainfall. So we can see that because based upon this climatology map, normally we can tell when the MJO is in a T3, 4, 5, 6, we can use MJO in the favorable phases. And when it is MJO in 1 to 7, it is unfavorable phases. So what happened, monsoon was almost similar in 27 each in the 2 monsoon years. But when we talk about the unfavorable phases, comparatively the large 30 days in the 1997, around 52 days monsoon was in the actually unfavorable phases. That actually what happened contributed to the very strong negative rainfall anomaly in the 2015 season. So that indicates that how these tropical climate modes, either El Nino, IOD, and because how the coupled ocean atmospheric interaction takes place, unless, again, I can tell that unless it is accurately captured in the climate model, it cannot simulate this rainfall variability over India. So this is the, I think again a quick summary. Actually 997, we can see that there is a, because we can tell that there is a, for example, ENSO diversity. 1997 is the actually Eastern Pacific El Nino, but 2015 is the kind of Eastern Pacific and Central Pacific El Nino. So that is what I can contributed apart from that, how this MJO, the position and strength of MJO contributed to the Indian summer monsoon, I can explain here. Next, actually, one of our work just published 2-3 weeks ago. So this is actually ISMR response to the two types of La Nina evolution. But whenever we talk about La Nina, we can see that there is a La Nina in the monsoon season. Sometimes the El Ninos, this La Nina is evolved from the warm Pacific SST anomaly or the cold Pacific SST anomaly. So with respect to that, the rainfall anomaly, observed rainfall anomaly also differs. For example, whenever there is a El Nino, actually there is a Gangetic West Bengal, parts of North Central East India we receiving, well, when this El Nino is followed by La Nina. But when is the La Nina is followed by La Nina, actually there is a difference is the rainfall pattern. So it is a kind of a dipole pattern, significant dipole pattern rainfall observers. So there are several, because this is the standard practice to check how the strength of the velocity potential in upper level, which can indicate the low level convergence in the lower level. So it is clearly indicating, but the detailed dynamics due to the lack of time I am not going to explain, but that can be found in the detail in our paper. But what happened, the model again, see you can see that whenever there is a La Nina followed by La Nina or La Nina followed by La Nina, climate models are successfully predicting the SST pattern and intensity to quite some extent. But again, when associated with the rainfall, again model quite challenges. For example, even though there is a observed rainfall in some part of India, but models, again climate models, there is a strong, there is a difficulty in capturing the rainfall pattern. So this is then a quick, the triple depth La Nina also we wanted to study, but I am not going to explain due to the shortage of time. But triple depth La Nina means prior to this, actually, 3 times when the cold SST, the Nino 3.4 index remained below normal for the nearly 2.5 years, 3 years. At the same time, all this triple dip La Nina monsoon, Indian monsoon was a normal to above normal rainfall. So, but again, where this is again telling in the MMCFS model, which is developed at IITM, sourced from CFS V2 and currently in operational, again is that models are successfully indicating this, predicting this Nino 3.4 index. But again, the rainfall diversity is still challenging. So this is now quickly I will move to the seasonal forecast activity of India Meteorological Department. As we know, the long range forecast at IMD is issued for more than 100 years, starting from 1888, starting from the Blandford when attempted to the forecast, long range forecast based upon the northern hemisphere snow cover, then followed by Walker's, and there is so much evolution of the strategy of the long range forecast. So currently we are issuing forecast for the different season, either summer season, winter season, or the monsoon season. Recently we using the multi-model ensemble. So, but as per the requirement, earlier monsoon forecast was issued as a 1 unit all India rainfall. Now later it was issued in the special pattern of the rainfall, but as per the user demand now, from the last 1 year, we are issuing the long range forecast even for every month of the monsoon season. A month ahead, we are trying to issue the long range forecast. So this is the quickly I will tell last three slides now. Yeah, this is the actually as per the multi-model ensemble for all the global models. We are most of the seasonal forecast model we are using. So this is the monsoon forecast issued in the month of April. So as many models were also predicting La Nina, so we predicted that most part of India is going to experience a normal to above normal rainfall during 2024 monsoon, and except few regions of the northeast India and central east India. So many regions of India captured this above normal rain for the western and part of India, but still again model successfully and to some extent, and up to this stage actually this monsoon rainfall is slightly above normal. And one good thing is this where how this good rainfall contributed. I mean, this year actually no break monsoon days so far, or as the peak monsoon months it is already covered. So this is the actually current status, because I am telling El Nino monsoon, this is the current status of El Nino. We can think that there is a cold Pacific, there is a kind of La Nina pattern switch, but it is not yet reached it's the La Nina strength. And as per the INCO's GODA's subsurface temperature, we can see that there is a cold surface in the central Pacific, but eastern Pacific, I think once by next month, it will reach to the strengthen, so that the strength of La Nina also could be developed. So every month, apart from the monsoon rainfall, we are issuing the El Nino and IOD forecast also, that which is we issued ENSO and IOD bulletin every month, and this is the latest forecast bulletin we are issuing. And also this is used for all the IMD Pune is a regional climate center, which is focused for the 9 South Asian country. We used this El Nino forecast and rainfall forecast as also. So most of our models indicating that, there is actually about 90-95% probability that during this winter the La Nina is reach to the peak intensity. So this is the quick summary. We know that ENSO remains a dominant climate mode, but it is important to understand how this interact with other tropical climate drivers. And despite advance in the climate modeling, accurately forecasting ENSO-driven rainfall is still remains a challenge. And while models excel in predicting the onset and the ENSO event, but still models there is a challenges in the complex interaction between ocean and atmospheric dynamics. So this underscores that a need for continued refinement of climate models to improve the predictive accuracy and enhance the preparedness of ENSO-related climate variability in India. With this, I conclude my talks. Thank you very much.
Thank you, Dr. Satyaban, for a very interesting talk and the vagaries associated with long-term prediction of the climate modes of variability and its connection to summer monsoon rainfall. Any quick comments?
Yes.
What is your forecast, the India Meteorological Department forecast for the coming northeast monsoon? Because this is the La Nina year, and it is supposed to have a negative correlation with northeast monsoon.
Yeah, we know that northeast monsoon also has a strong correlations, but unlikely to the summer monsoon, it is opposite correlation of the northeast monsoon. But as we know, this IMD's official forecast will be issued by the end of this September, so it will be better we'll wait for that time. So by around 28th or 29th of September, we are going to issue. Now the process is going on. We are concluding all the evidences and possible climate models and climate data. So official forecast will wait for that one.
Thank you.
Wonderful. Thank you again, Dr. Satyaban. And this officially concludes this session. And I would like to thank all the speakers since morning. Excellent talks by everybody, including the keynote speeches from Dr. Prasad and Dr. Ramesh, and also all the invited speakers. They are showcasing amazing research that is being conducted in India, and definitely no less than any international seminar, these kind of talks you will get. So I definitely feel proud of all the contemporaries of mine, particularly coming here and giving their talks, and congratulations to all of them. Back to organizers.
Yeah. Thank you, Mr. Chairman. Yeah. To honor this morning's speakers, I request Professor Bhaskar Rao Garu and Dr. R.R. Rao Garu to come onto the stage, and also I request Dr. Jnanaseelan and Dr. T. Narayan Rao Garu to come onto the stage. Most of you must be thinking why the other speakers. Those who have received mementos will not be given again, as per our anyway convener. I request.
Not shortage of mementos, I guess.
I request Dr. R. Rao garu to honor Dr. Jnanaseelan and Professor Bhaskar Rao garu to honor Narayan Rao garu. Now we break for the parallel sessions. I request all of the delegates to go to the respective sessions for their talks. The session here will be chaired by Dr. Jnanaseelan. The session at Sagarika Hall 1 about the dining hall will be chaired by Dr. Narayan Rao garu, and the session below this will be chaired by Dr. Sandeep Patnaik of IIT Bhubaneswar.